Welcome, everyone. It's such a great pleasure to have Vijay Balasubramanian. He's going to give us three data impulses lectures. Today is the first of them. The next one is tomorrow at 11 a.m. And the third one is on the Thursday at 11 a.m. The title of his lectures is Quantum Chaos and the Complexity of Time.
Oh, I intended to change the title because I gave you a different title, but that's okay. I'll go with this title also. Great. Thank you very much for inviting me. It's great to be here in the TIFR group, a fabled group in the field. So that's really great to be here. So since it's three lectures, I'm going to give us a comprehensive discussion of a series of developments with various collaborators over the last 6, 7 more years, 8 now years. And my interest in sort of complexity of time evolution, etc., actually started in collaboration with Onkar here and with Arjun Kar and Matt Cross, who were students in the group at the time. There was a really wonderful dynamic, you may remember. So there was there were 4 of us. We were talking all the time on the blackboard. Every day we'd come in, and there was always an argument as to where to go for lunch until Arjun made a little electronic app that would randomly pick which lunch truck we would go through. And so that settled the arguments. Okay, so that was a very nice time in the group. Okay, and then there's a series of papers with Javier Magan, who's now Barcelona. He used to be in Bariloche. Pavel Saputa was in Stockholm. And Austin Wu, who was just an absolutely great graduate student. And then since then, I've been writing papers with a bunch of other people: Johan Simon, Johanna Edmenger, Rapindranath Das, Zhou Yu Xian, Paolo Minandi, Jonathan Carl, Kathy Lee, and Herman Verlinde. So there's just a comprehensive list. I'm not going to mention each person at each time, so I thought I'd mention them at the very beginning. Okay. So what is this set of lectures about? So really, it's about generally thinking about complex dynamics and quantum systems. This is a topic that has become interesting in physics in many different fields of physics. So, for example, famously, it is a challenge to characterize precisely what is meant, if there is a precise characterization, of quantum chaos versus integrability. This is partly because the Schrodinger equation is linear, because it's linear, right? It's just a matrix acting on a state vector. And so because of that, normally you think of chaos as involving some essential nonlinearity. So exactly what you want to mean and how it corresponds to classical, the classical notion of chaos are things that are actually not settled yet. And so what is meant by integrability is not settled. And so we'll see. You might think that chaotic dynamics is somehow complex or complicated. Well, what does that mean? That's one reason why you want to think about these things. In quantum computation, this has become important to characterize, famously, there's a whole branch of computer science, which is complexity theory, how complex is a computation. And if you regard time evolution as a computation, then this is something you're interested in doing. And then there's, the discussion in condensed matter physics of dynamical phases of systems. The systems are out of equilibrium and interesting things are happening. And you might think about characterizing different phases of dynamics by how complex or complicated the dynamics is. And finally, in quantum gravity, which is, I guess, our neck of the woods, there are many puzzles about black holes involved in this. So just to give a flavor or motivation for this series of 3 lectures, I'm going to pick this one, because that's, I guess, the core interest of many people in this room, and discuss how questions of complexity come into play in that area. And then we will start developing some ideas. Okay, so I want to discuss some puzzles about black holes. I think everybody in this room knows what's a black hole very, very well, but I just want to set on the table what I'm going to mean most of the time. So as you well know, at the classical level anyway, a black hole is a solution to general relativity, which is a vacuum solution, which has a metric like this is the Schwarzschild metric. You know that R equals GM looks singular, but it isn't, it's the horizon. And you also know that there is, in fact, a singularity revealed by the conformal diagram. Let me make sure, since I may use these more later, everybody knows how to draw a Penrose diagram, right? If not, you should learn how to draw a Penrose diagram. So this is the eternal black hole. This is the one we'll think about most of the time. For convenience, here's one asymptotic region, another asymptotic region here and here. And on this slice, it's connected by a wormhole. The wormhole gets longer as time passes and ends in a space-time singularity. So Okay, you can also make these from stellar collapse. And famously, it has a thermodynamics. A black hole is an entropy area over 4G nu. So many of the puzzles of the black holes concern this kind of thermodynamics. So in particular, if it has this much entropy, you might ask, you expect to see e to the entropy states in quantum gravity. So why can't I see them? Right? So a potential answer to that question goes like this. So here we're going to try to get more, the tools we're building at some level are supposed to eventually help us with making this concrete, these kinds of points that I'm going to make concrete. But I would like to give a qualitative argument here that maybe you can't see the microstates of black holes simply because they're too complex. They're somehow structurally random. And you have a hard time seeing that using the normal kind of semi-classical or effective field theory probes that you might use. So I'm going to give a qualitative argument about this. And at the very end, I'm going to suggest that the tools we're developing may help us to give a more quantitative argument about things like this. So I'm just setting up in this in the motivation series of qualitative arguments about this kind of thing. So here's a sort of semi-qualitative argument. Here's an old argument. So suppose you have a black hole, let's say in the anti-de Sitter space, which has a mass m. So if you believe the whole entropy thing and the ADS CFT, then you should conclude that since the ADS 5, it's dual to SUN Yang-Mills, SUN D equals 4 super Yang-Mills theory, according to the usual ADS CFT correspondence. So you're expecting to see, well, okay, so you should find states in that theory with a mass, with a conformal dimension, which is mass times the scale, ADS scale, which goes like n squared. And so basically, we should be finding that a microstate of the black hole, which of course contributes to entropy, should be related to some state which you make by a very heavy operator acting on the vacuum, right? So so what do such states operators look like, right? Sandeep, how are you?
Very good.
Great to see you. I've promised to make fun of you for being late.
So sorry.
No, I'm teasing.
Great to have you.
Yeah, great to see you. There's a seat.
Yes, sir. Just come.
Yeah, if you sit here, you can heckle me more effectively. Oh, have some tea.
Yes, that's fine.
You want some tea? No, have some tea. I got some tea.
Thank you.
This is the good thing about giving talks with old friends.
Well, this is also inimitably Vijay.
What is?
Okay.
Yeah. Okay, so let's see. So how do you make such a heavy operator, right? How do you make any operator? You're supposed to take the fundamental fields of the theory, in this case, gauge field, some adjoint scalars, some fermions. You multiply them, and you put some traces and everything to make it gauge invariant. So you have to sprinkle some traces. So here's an example: trace x, x, y, x bar, z, z, something like this. So what do such strings look like? So let me assert that almost all big operators that you can make in this way must look like random polynomials in the field. Why is that? It's because almost all, if you try to make a very long string out of some finite alphabet, it's a theorem. Almost all long strings look random, right? So you know that they're going to be structurally complex in this way. So in particular, you can do this kind of thing. You can say, suppose I pick some operator and I write down the distribution that some random letter in that long string is, let's say, x or whatever else, right? Some letter. So, and let q of x just be 1 divided by the alphabet size, right? So it's a uniform distribution. So if I take very long operators like this and compute the probability that you have a particular distribution of different letters, of a's and a mu's and x's and y's, you'll find out it goes like e to the minus n squared times the relative entropy or Kullback-Leibler distance between relative entropy between the distributions p and q, right?
I didn't understand. What is p and q?
Okay, so p is the distribution of symbols appearing in your operator, right? And you've picked your operator randomly from the bag of very big operators. Q is the uniform distribution. So the statement I'm making is up to constraints. There may be constraints. So suppose the thing is charged, then you must have a certain number of things of a certain charge and things like this. So it's a theorem in classical statistics, but this distribution is suppressed as e to the minus length of the string times the Kullback-Leibler distance. I'm not trying to be super precise because, there's some details, like, for example, you have to stick in traces or something to make this to make it gauge invariant. There's actually, if you make the operator too long and stick a trace, then it'll break up into, it'll break up into multiple traces. There's some issues, but I'm sort of ignoring those at some level. I'm just basically saying that this is a theorem at some level with some details to be fixed. But most black hole microstates are just structurally random, they're complex. So they're going to be extremely difficult to sense. If you take a small probe, like a small probe looks like XXY, and you take a very long operator, there will be equally many places to match the small probe. If I try to mechanically do a calculation, you put a correlation function, what do? You put X's and X bars and Y's, you contract X with X bars. That calculation will look structurally identical for most long probes. For most short probes, simple operators, probing this long one. So you're going to get essentially a universal answer. In other words, you can't tell what the microstate is using a simple probe, right? So this suggests...
Sorry, what you say is of course true, but just to understand that formula, probability of P, and then it involves the relative of P and Q. Yeah. So what's Q doing here?
Because you want the distance from the uniform distribution.
From the
uniform distribution. Okay. So the typical state is uniform distribution. These are large deviation theorem.
Okay.
It's called Sanov's theorem. It's a large deviation theorem in classical probability. That's all I'm using.
Thank you.
Yeah. I'm trying to be semi-quantitative. As I said, I think possibly just before you came in, I'm going to give a series of qualitative arguments as to why people should care about complexity, whatever that means, and trying to make the notion more precise. So I've made some kind of argument here that these very big states are somehow complex and hard to probe using simple operators. Here, complexity is being a little bit conflated with randomness. It's not exactly the case. We'd like to be a bit more precise. So all of these arguments have this kind of semi-quantitative character in the beginning. Okay.
Sorry, what is the probability of what items? Is it
okay, yeah. So what this is so suppose I pick some letter here, the fifth letter.
Yeah.
And I ask you, what is the probability that the fifth letter in this string is a mu, x, y, x bar, y bar, psi, all the possible symbols I could use. So in the typical state, the probability that any given letter in this long string is any one of the letters you could have used is the same. It's uniform in the typical state. In the operator that you picked, so actually, sorry, I take that back. It's not the probability of the letter in the fifth place. What you do is you make a histogram of how many times X appears, Y appears, Z appears, psi bar appears, all these things. Make just a histogram.
Okay.
That is some histogram. You compare that histogram to the uniform distribution.
Yes.
So Q is the uniform distribution.
Yeah.
And this is simply a statement that almost all long operators will have a uniform distribution of symbols in them. And this is a large deviation theorem saying just how likely you are, leaving aside issues of gauge invariance and symmetries, just how likely you are to have a deviation from the uniform distribution of fields in the overall operator you make. Yeah. I'm trying to leverage a statement about the actual physical construction of operators from elementary fields.
So if P is very close to uniform, then this probability is order 1, and if it's anything else, then it's exponentially suppressed. That's the point.
Yes. Yeah. It's exponentially suppressed in the dimension of the operator. So it's like n squared, even among n squared, going down super quickly.
Right.
Okay. So there's a similar thing you can say, which is, you may ask, why is the interior, now here's another puzzle. So why is the interior causally disconnected from the exterior, right? And usually, we'll give some dynamical explanation of light cones and everything. Okay, but there's another way of thinking about it, which is that actually if you think in this way, that it's just simply things are hard to detect because they're very complex, then actually the problem is that we never think about waiting long enough, or we rarely think about waiting long enough. If you wait long enough, you should be able to read it up. Here's an example. Here's a semi-qualitative quantitative argument again to this effect. So suppose you have a black hole of area A. So this is so I should have said this is with Jan de Boer, Vishnu Jajala, and John Simon from many years ago. And this is with Don Morolf and Moshe Rosali, also from, God help us, 20 years ago. Okay. Time passes. Okay, so suppose you have a black hole which has area A. So that's entropy area over 4G Newton. So what does that mean? In practical terms, it means you pick your energy resolution, whatever that may be, and we expect something like e to the s times some constant. So e to the area over 4G Newton h bar states. That's the meaning if you think it's an entropy. So now you can argue, in quantum mechanics, up to symmetries, each microstate will have a unique energy, right? Because they'll mix. So that must tell you it's a theory of gravity. The energy of the state is encoded at infinity, right, in the mass formula. So it must be that if you measure the mass precisely, it'll tell you the state. So the fact that we always keep saying that you can't find the state, you can't look at the inside, must mean it's somehow difficult to measure the mass. So in what way is it difficult to measure the mass? Well, okay, so mass is measured at infinity. Asymptotic observers can detect it. But the energy gaps between these microstates must all go like, your measurement resolution, which is going to go like e to the minus area over 4g Newton h bar, right? Tiny. So now you know from elementary quantum mechanics, delta T, delta E is bigger than or equal to h bar, which means to get energy resolution of this precision, you need to really make the measurement over a very long period of time. You can't help it because it's quantum mechanics. So the time scale will go like e to the area over 4g Newton h bar. Right? A message that in recent times has been pounded into us in other ways, like the page curve recovery, all these things. This is the time scale. And I think the real reason this is the time scale is the time scale to resolve the differences.
Sorry, this is much bigger than the page time because the evaporation time goes like m cube or something like that in 4D. And the page time is when a fraction of order.
Oh, yeah. Okay, I'll take that back.
Like exponential.
This is exponential in that. Yeah. Okay, yeah, absolutely. So I withdraw all these last statements I made and instead say the page time tells you the information has come out. It doesn't tell you can measure it as in, identify the state. It just tells you it's out there, which is a different question. It's a less intense question. But now tell me what the state is. Yeah. Withdraw. And I think, thank you for the correction. Yeah, both of you. Absolutely. So what that tells you is that G at h bar goes to 0, basically. Or
it's still the time scale at which wormholes become important.
Yes.
That's right.
Yes, it is the time scale at which wormholes become important. Yeah, exactly.
One could set up some external.
Arguably, there's replica wormholes, and that happens at a much earlier time, like polynomial.
Yes, that is actually
that's different dynamics, I guess. But
I want to say you could set up the thermophile double by pumping.
Yes, that is exactly the conflation I was doing in my head. The page curves resolve the wormholes. This is the time scale. But actually, that's a different thing because that's the replica wormhole. So there's some differences. That's why I explained exactly. So, but it's still the case that if you were actually doing a single black hole, evaporating it, and trying to identify the states in the eternal black hole, right? This is the time scale that would be relevant. And here's an argument for that, which also means that if h bar is going to 0 or g Newton is going to 0, in other words, you're doing classical gravity, then you can't tell the differences. And it is perfectly correct to draw this Penrose diagram with something there which you can't resolve. You can't. So it's correct. But also, clearly, if you wait enough time, you can tell what's going on. So maybe this picture was wrong. And indeed, I think the spirit of the current time. So, the way we usually work is we start with classical physics and we try to quantize it. Now, of course, it could be that when you take the classical limit, you get some misleading thing out of it because it's a limit. And then backing off from that misleading thing could be a complicated business because you have to identify what was it that you left out in the quantum theory when you got there. Like some of the recent discussions that sort of sporadic states, when you take the large n limit, do you drop them or not? It's like that. You come to some limit, and then if you've left out something, it's hard to recover by quantizing the thing where you left out something, right? So I think this is the struggle that we go through. Okay. But anyway, again, the idea here is that it's sort of very complicated in the sense, in the amount of time you need, And when you're doing computational complexity, a computation that takes a long time, this exponential time would be considered complicated. So again, it's some sort of complex computation. So here's a third puzzle for which I won't actually have any. Well, okay, fine.
Sorry, Vijay, you sort of suggesting if you were to probe the interior, you draw that line and then you have the interior. If you could do something complex enough.
So that's that's what I was saying. And here I'm conflating complexity with having to do it over a very long time because that involves many, many operations. Actually, we have some papers arguing that if you have a single probe that is complex enough, this is our error correction, the quantum whatever, that's a toy model, that's in JT gravity and everything. You can, in fact, probe the interior, or at least some aspects of the interior, if you use a complex enough probe instantaneously. Right, so you can do instantaneous complexity of probes, which is what the first thing I was trying to say was, or you can just take a simple probe and just do it enough times, right? So to say, measure it over enough time, and then that's already that's also a copy. You use the dynamics to produce the complexity of the measurement that you need. Would be the idea. Okay. So yeah, I'll see if I have time to talk about. We're using that. Okay, I'll see the third lecture this time. So third puzzle that I would like to similarly talk about qualitatively. By the way, just because normally I'd speed through this, but since you told me I have 3 lectures, I'm taking my time.
And since you have 3 lectures, I'm sorry. So
Sandeep, it has nothing to do with 3 lectures. You know perfectly well you would interrupt me regardless until I gave satisfaction.
when do we have the opportunity, Vijay, once in 20 years to do that? Anyway, never mind. So the question I want to ask.
So invite me.
The question was, I didn't follow your papers on JT and so on, but do you folks, or do you have controlled examples where, you do something very complex instantaneously, and then you show that a wormhole opens up and a bomb goes off deep inside or something? Are there controlled examples?
I don't think that is the character of the calculation we did.
Our paper was sort of saying the opposite, which is that if you do complex enough things, then you can't affect the black hole. But I mean, we can.
Can you turn it around and have I'd love to investigate, being able to probe the interior in precise but complex ways, and see what it takes.
There are these things like bets. Okay, now we can debate this, but there are these things like bets and so on, which at least on the face of it seemingly.
Okay. Yeah, I would give that same answer, but I think it's very, very weird to say that you make a measurement out of infinity and somehow it's set up a bomb on the inside. There is, I think, probably a age-related divide in the field. I think if you're below a certain age, you're brought up to it, and so it seems like, why not? But if you're older than a certain age, it seems a bit crazy.
No, exactly.
And requires further evidence.
Exactly. Since I think you belong to that, I'm not sure that age group. Therefore,
maybe you're calling me old, but
in that case, you become old. Because if you're younger than a certain age, they've all drunk the Kool-Aid. They heard it in some school, so it must be true. So but then if you talk to certain other people, you Don or all people, and you say, "What does this mean?" And you say secretly, "I don't really know what they mean."
Yeah,
right. I mean, so it's a bit confusing.
Yeah.
It's a bit confusing. I think there's some misinterpretation personally going on. I mean, clearly, a complex operator can be used to probe the state. Right? And I have no problem with the statement that the complex operator applied to, let's say, the Hawking radiation, something can decode something about the state. But normally when I think about the, say, the EPR paradox, I don't think of it as, doing something instantaneously the other side. Indeed, it doesn't. Otherwise, you'd have a causality.
Exactly.
So this feels to me a lot like EPR, except that it's done with so many quanta, right? So I don't completely understand some of these statements. So I just do my usual and ignore it and keep doing things. Understand. There is one paper I wrote with Chitran Murdia, and which I won't talk about, and one paper I wrote with Tom Yildirim, who's a graduate student at Oxford, which have the following character. So we've been working on trying to build these microstates for black holes using dust shells and what have you. So you could ask, well, you have an explicit model there of what these what's there. So then why can't I do an explicit calculation using wormholes and what have you, what the state is? And you can. It's very interesting. A little bit like what I was saying here, right? You can show that at least in the when you take leading saddle points and everything, almost all probe states, including very complicated dust shells and everything, will give you universal answers because of the way everything works out, except a particular very special probe. It's the anti-dust shell. So that's the interior shell. The states are made of the dust shells. And so the anti-dust shell will give you a big response. But you don't know to try that. Until you know it. So it's very much like a P versus NP problem.
Mm-hmm.
If I propose the answer that this is the state, you can check it very, very easily. If I don't propose the answer, it will take you a long time to find it. You can Grover search a little bit to speed this up, but it'll still be exponential, right? Grover search has a square root, and that's it. So it's a P versus NP kind of thing. It's checkable, so that means the information is there from infinity. In an explicit way, there's a wormhole calculation you can do and just show it, but you can't find it from scratch. So there's two papers, much ignored, but kind of interesting. No, not much ignored. I mean, yeah, it's kind of interesting. I think it's sort of okay. So another puzzle that we could set up is, of course, a major unsolved thing for us in the field is what is the singularity? And so usually we say you come within Planck length of the singularity, curvature gets very big, quantum gravity corrections become important, you should worry about it. So another possible answer, which we will discuss in, I think, the third lecture, is that actually that is not the right view. The right view is that you should never have drawn a classical picture past a certain point. Same mistake of drawing a causally disconnected interior. So the dynamics, the chaotic dynamics, makes the quantum gravity wave function exponentially complex, quantum complex, and so that a simple continuum classical description is just wrong past some time scale, right? And so you should have never drawn that part of the geometry at all. So we will try to give some evidence for that picture using the tools that we will develop, and we can discuss whether that view makes sense.
And just to, I mean, we'll of course wait, but that boundary where up till where you can have a classical geometry
we will end it surprisingly early.
Is surprising.
Yeah, surprisingly early. We'll discuss the time scale in a bit, well before the Planck distance away, right? So this is also something related to some things we have been working on with Vivek here, right? And Onkar also has papers on Wigner negativity and everything that have a similar kind of flavor, and we have some papers on using these tools of complexity that point this direction. Needs to be nailed, but there's some vector in the thinking. Okay, so a whole bunch of puzzles, and then I'm going to put the puzzle that everybody else cites, which is that, if you take this eternal black hole, draw a line through it, so that's a spatial section, and you just keep going up this way, on this side, and leave this here, then the time is evolving, and there's an Einstein-Rosen bridge here. You measure the size of that, and it grows. That volume of that thing is a diffeomorphism invariant quantity. And usually in ADS-CFT, any invariant quantity on one side should have a dual that's also invariant. Gauge invariant is gauge invariant, some kind of relationship of this kind. So you expect that this volume has some corresponding object, which is gauge invariant, in the dual CFT that calculates it. And in the general theme of how do field theories produce geometry, it's a good thing to understand. So one sort of slightly weird thing, is that this volume keeps increasing for a long time, indeed forever actually, certainly well past the thermalization timescale, where in the field theory you'd normally say everything has been equilibrated. So nothing increases anymore typically, or changes really, because it's equilibrated, right? So there is a conjecture to the Susskind that the volume of the Einstein-Rosen bridge is dual to quote-unquote the complexity of the dual state. The problem with this conjecture, as stated, is no one gives a definition there of what complexity means. So it's a null conjecture, because you actually, if you say A equals B, you have to have a definition of A and B. So we will try out a couple of definitions of B, namely of the complexity. And for one definition of this, something called spread complexity that we defined, it is a statement, a proved statement, that in JT gravity it's equal to the volume of the wormhole at early times. And it's also a demonstrated statement how and why that breaks down at late times, because the state becomes very quantum mechanical, which will be the basis of my comments about the singularity later. Okay, so we'll show you that in lecture 3. So suppose you agree that it's, volume is complexity. Actually, that makes two predictions that we will also be interested in thinking about. One thing is that if this volume is related to some notion of complexity in the field theory, well, this volume keeps increasing linearly for a very long period of time, linear growth. So that predicts that the appropriate notions of complexity will have linear growth for a very long period of time. And that's not actually obvious when you think about time evolution as a quantum computation, why the complexity of the state or whatever it is you want to talk about will grow linearly over a long period of time. So that's one thing. And there's a reverse prediction. If you actually believe CFT maps to quantum gravity and volume equals complexity, then essentially any definition of complexity that anybody's ever come up with for quantum states will tell you there's a maximum complexity. Another way of saying this is you've got two qubits there's only so much stuff you can do with 2 qubits, right? Beyond a certain point, that's it. So in particular, if you have n qubits, there's some exponential number in the n qubits that in any definition of complexity that anybody has devised, there's some exponential, and that's the limit. There's no state that's more complicated than that, right? So at least if you're not in the continuum or you have some energy gap and you anyway bound. So that means if it's true that volume is complexity, that's a prediction that in the quantum theory of gravity, as opposed to the classical theory of gravity, the volume should saturate, or the analog of volume in the appropriately quantum mechanical theory should saturate at late times. So that's another thing we would like to see and understand. And we will again provide some evidence for that in this identification. All right, so that's the qualitative introduction. Good. So the question is, for any of these things, you have to give some more meaningful notion of what complexity is. So that's going to be the all of today and part of tomorrow, and then the remainder of the second half basically will be applying the ideas as we develop it, all of these things. So I will develop this slowly. So it's all obvious a priori what complexity should be. We're making up a notion, and different notions can be made up. And some will be useful for one thing, some will be used for something else. So it's useful, I'm going to set out. So people basically in the field, in our field, have gone after this essentially in 2 major ways. There are also subsidiary ways, which I don't have time to talk about. One of the major ways is to think about dynamics as computation. So basically, we're going to think in 2 ways. One is complexity is the same notion of complexity in computer science. And another way we will think is that complexity being somehow related to ergodicity, which is, which by the way, need not a priori, that's one possible notion, right? It could be also that complexity, quote unquote, is a kind of multifaceted thing, right? Who says we use one word, but could mean many different things, like consciousness, right? It could be many kinds of consciousness, right? Or intelligence, right? Okay, could be many things. So like that.
If you're after a bulk quantity, then it's one
For
particular.
that, it has to be one thing, which is why we'll talk about different things, because the other notions may be useful for chaos versus integrability, for dynamics of complex systems. The other notions may be more useful, but it is going to turn out that for the bulk map, so far we have one candidate that matches in one case, right? So we will talk about that mostly, because we're in this community, we're interested in that, but it's useful to put the other notions on the table. Who knows, right? Maybe those become more useful at Sunday today.
And then one case where it matches is the
JT. Yeah. Everything works in JT. I think we should stop calling it JT gravity. We should call it JT not gravity. Because there's no gravity in 2 dimensions. So we're pretending.
What do you have the gauge consider?
We are totally pretending. But it does capture some features. So, for example, the thing I like about our shell states as microstates and everything, essentially exports many of the kinds of ways of thinking from JT gravity to any dimension you want. And I just prefer doing things in higher dimensions.
It has a gravitational path integral. That's what you're importing, right? Like that's the feature.
Yeah.
That's gravity.
Is it gravity? There's no gravity in 2 dimensions. Come on. Right? I mean, it's like this little 2x2 matrix. All the gauge constraints mean there's no dynamic. Okay, anyway. Was that?
That's the part. It's wormholes.
Yeah. Okay, it's a lobotomized form of gravity.
Describing an extremely precise way, fast rotating black holes in the sky and their low frequency response.
I think you guys are defending this because you've spent time working on it.
Oh.
That's not.
Yeah. You're making sure that your life is meaningful.
It's the nature of our field, Vijay.
I know.
More than can be said about most of the work done on black holes in the community. It doesn't pertain to fast rotating black holes at this time.
Well, there are very few.
And JT does describe that. Go on.
I was going to say, it doesn't apply to them because they're not as fast rotating as you need for JT.
Yeah.
Right, but I'm saying at least there's one physical context where JT does describe something.
Does it? Are you sure?
No.
Are you absolutely sure? Wait, it's going to turn out that it's not going to quite do the right job. once they do the actual measurements, which they won't in our lifetime. No, seriously, it does sort of describe it, but that's a few limited cases.
Oh.
Okay, anyway, I don't want to argue about it.
Oh, yeah.
Okay, if it offends your sensibilities, I will continue in this audience called JT gravity as opposed to JT not gravity. And I work on it too, occasionally when I'm forced to by a referee. I've actually had referee reports where we write papers saying, we have shown this for black holes in any dimension that rotate in any way, that don't have to rotate anything. And the guy writes back saying, can you show this in JT gravity? It's like, oh, you people, you're stuck. Liberate your soul. Think about the world. That's this. Literally, I get this kind of report. Right? Can you repeat this in JT gravity? Don't you have a life? Okay. So what we do, we repeat in JT gravity, which we can, because actually it's more general. Okay, good. Moving on. So let's first discuss dynamics as computation. Right? This is the first approach, which is not mostly what we will do in the rest of this, but this is an important early development that I feel is going to come back. So I'm sort of repeating this. So right now people are ignoring it because it's hard. Right? So, okay. So if you were going to make up a notion of complexity, what would you do? Well, if I was talking about classical physics, if I had a dynamics of a bunch of gas molecules all moving around independently, bouncing off each other independently, and things like this, it could look a little bit complicated, but they would sort of all move around. I would call that a simple dynamics, simple local rules. Now, if I have a bunch of particles, they do something, and after a while, you walk out, right there, see? That's you. This is of you. If you walk out and there's a bunch of particles, we would say it's a complex dynamics because there's lots of correlation, self-organization, emergence. These are the collective effects is what we tend to call complex dynamics. So in quantum mechanics, if you want to take this kind of view, that structural complexity of the evolving state is what makes it complex or not. If I have a dynamics, the usual Gaussian thing kind of spreads out, gets a bit bumpy, pretty straightforward, right? But if it becomes very bumpy with short range and long range correlation and entanglement at the same time, very complex structure like that, then I might say it's a complex dynamic. Because it's a bit confusing how you can make from this simple state something with multi-scale entanglement and things like this. It could be difficult to do. So you might think something like that as a complex dynamics.
So say in this last part, what was this?
This?
Yeah.
I'm just trying to say that if I have a simple Gaussian state, and it turns into a wave function with lots of, at least in position space, lots of short and long range correlation across many scales of, highly variable structure across space and stuff like this. I might be tempted to say it's complex dynamics. The reason I'm saying these qualitative things is I think actually another structural problem with our field is I think there's a tendency to start with extremely complicated bits of math and just instantiate them and say, oh, great, I've done a fancy piece of math. I think what the way we should be thinking is, look, you want to describe the complexity of something, you should make something up. And then see, after you've made it up, whether it compares, whether you can borrow bits of the literature to do the thing that you want to say. We're trying to express a concept. It's not obvious that previously expressed notions of complexity or whatever else are the things you want to say. You should just make up something to express the thing you want to say. That's what I'm trying. That's why I'm giving this qualitative kind of thing. Anyway, in this case, there is an intuition that we can borrow from computer science. Onkar doesn't look happy.
No.
Oh, okay. You're doing this.
No.
Okay. So there is an intuition from computer science that's related to what we just said, that complexity somehow counts the size of the algorithm needed to assemble the object, like how many gates you need, or how deep they have to be, or wide, something like that. And so this has been going on a very long time. So the Ur kind of intuition here comes from Kolmogorov, actually, and it says that the complexity of a sequence is the length, the shortest program, say on a Turing machine, required to make it. From by this definition, pi is actually very simple, even though it looks complicated because it's a short program to produce pi. And root 7 is simple because it's a short program, but a truly random sequence will be complicated. And recall, this is a little bit like a black hole microstate operator. So this is like, a compact representation of pi is a short program that makes it. So it's simple. A random sequence just can't be compressed. So it's complicated. So that's a little bit like what I was talking about for the black hole operators. Although we will not do this, I have some idea in the back of the head about thinking about the structural complexity of states and operators and trying to understand what that is and relating it to this kind of problem.
That's one thing.
Yeah.
I mean, sometimes, at least I get worried or confused as to what is the starting point. That is, like maybe in computer science, that is clear.
That is an excellent question. That has parts of those questions involve what is the basis set you use and things like that. We're going to come to that. So if you would re-ask in about 3 or 4 slides, we will revisit this question. Yeah, because
in the volume of complexity, that question doesn't answer.
Well, you're using a particular Turing machine architecture. So if you want the number, you see. Okay. So that is why these people, the way they work is they won't actually tell you the complexity. They will tell you a scaling law. Because the scaling law will be relatively universal over different models and over different starting states. But for us, if we want to match to something like volume, we need to put our money down and specify what is if you want to compare it to this kind of thing, you have to specify the architecture. You don't have the option of just saying, I'll give you the universal scaling. That's not going to be good enough. So we have a higher bar. Okay, great. So there's another version of this, which is called stochastic complexity, which you're very familiar with, where if you have some sequence of symbols, then you would say the complexity of the symbol, the message, is the size of the shortest code required to represent it. So this is like, if I have an image with structure in it, like people, then you can JPEG it to get it to be much smaller. You can use the lenticle zip algorithm to compress text to be very small. Hey, Shiraz, how are you? Good to see you. Nice. Excellent. I would think.
Oh, okay. This is on camera.
No, you shouldn't say anything embarrassing.
Warning.
Yeah. I've already said various embarrassing things and embarrassments, so it's okay.
So sorry for being late. I had a promotion meeting. I did. That's
a likely story.
Yeah, all of this is on camera.
Yeah. Already teased him. Fair is fair. Okay. So for example, JPEG is like this. So is lenticle for compressing text. And again, the intuition here is you pick the smallest. So this is going to come back, right? You take the thing, this complexity you want to measure. You consider the formalism within which you're measuring it, and you consider the shortest, smallest description of the thing within that formalism. So the choice of formalism, you have to motivate while you're doing it. But there's the shortest description in that form. We'll come back to that. So this is a recurring theme all the way from Kolmogorov. For example, for circuit complexity, either classical or quantum, you have so many bits. It's an algorithm now that I wish to perform. And then you have to find the most compact description of the algorithm within the formalism you've picked, which is you've picked a particular gate set and you want to put it together to make this algorithm. Well, that was the complexity of the algorithm. So all of this involves pick your poison, namely your formalism, and you have to have a motivation for doing that. You motivate that, and then you say, make the smallest one. And that measures. Okay, so that's the idea. So there is an ambiguity. This is what you were referring to. The size will, of course, depend on the computing architecture. For example, the particular Turing machine design, details, the decoding algorithm, etc., or the gate set. And so usually in computer science, you just say things about how the complexity scales with the input size, and then you try to prove that over some classes of our architectures, the scaling is invariant. So you have some meaningful notion if you can't put your money down as to why you should pick this or that architecture. Okay, so that's what people will do. And for us as physicists, if you want to apply this kind of idea, there's some feeling you might have that, for example, locality in space-time maybe suggests some canonical aspects of what makes things simple or complex building blocks. So, for example, it seems natural that if you have gates that manipulate nearby qubits, somehow that feels more local qubits seems simpler. If you have gates that manipulate fewer qubits, that seems simpler. Certainly in the context of quantum computation, that's just true. Right? That's local, bounded operators are somehow more simple to build. Okay. So using all of this, remember again, we're going after this this idea of we want to give a definition of this quantity and then somehow try to apply it to some of these problems in quantum gravity and and statistical physics and so on. So the idea, then, is from computer science, the minimum number of simple pieces required to build X, right? So the minimum number of simple Lego blocks, that is the complexity, and we have to ask what simple building blocks. So for us, psi is the state is characterized by a vector in a Hilbert space, and the time evolution goes as, you act with e to the minus iht, h is permission. And so there is a idea, and so one way of thinking about this would be to say e to the minus iht is a computation. So please tell me the minimum number of some kind of gate set that you need to do this, and that could be some sort of characterization of, it's certainly a characterization of the complexity of simulating the physical dynamics on a quantum computer given the gate set that you can. But in that sense, it's meaningful. So Nielsen famously had a proposal for a more sort of continuous description of this, which seems sort of more appropriate to the kinds of physics questions we want to ask. So it's sort of not all discrete and gate setty. So you say to yourself, this is the unitary group, it's complicated fiber bundle, but anyway, here's the identity. And then you run the time evolution. It goes from here to here like this. Mm-hmm. And you say that I'm going to tell you that the complexity of this process was the length of the geodesic between these 2 points in some particular metric that penalizes complex operators. By complex, we might mean non-local or many-body, or you have to pick a definition of what you meant by complex, okay? The reason why he proposed this, he proved that this quantity, what you get out of this is geodesic length, is polynomially related to circuit complexity. Namely, if you were to pick some particular gate set, this geodesic length will be related to that size of the circuit, number of gates you need in the circuit, by some up to some polynomial in the problem size, right? So the size of the input.
So you take that continuous evolution, you try to implement it, say, on some quantum circuit, and then the circuit complexity gets...
It will get related to this up to some polynomial. There's some multiplicative polynomial in the problem size.
The gate set that's relevant in that case would be like exponentials of your simple directions.
Whatever gate set you pick here to be simple, that is the gate set that is supposed to be simple here. You are only allowed to use those gates. As you say, it's exponentials of the simple tangent directions. Maybe. So in practical terms, you've got to define a metric on SUN, right? And so the metric will look like this. You put some identity in the simple directions. This is a little bit like the Cartan killing metric, except you modified it a little bit. What you've done is in the directions that are deemed complex, which I'll put dots for, you add a 1 plus mu, where mu is going to be going like, maybe I didn't write it down. It's going to go like the size of the Hilbert space, so a big penalty. You can pick other penalties. You can make the penalties that are dependent on how complicated the operator is. So for example, if you think that 1 and 2 body is simple, 3 body is a bit more complex, 4 body is a bit more complex, etc., you can grade this in some way by that. Adam Brown in particular has spent some time trying to think about different metrics that can be used and whether they give the same result or not. So he has spent some time thinking about it. But this is what Nielsen did, so we'll just stick to that.
Gij is a metric on tangent space of unitaries, which means on Hamiltonians.
Yes. So how do you solve the geodesic equation? Well, you write it down. So you can write this down in something called the Euler-Arnold form. So here are vectors, on SUN. So this is work with Onkar, actually, and with Arjun Kar and Matt DeCross. I learned all of this from them, actually. And so there's something called the Euler-Arnold form that you can write down. So these are the FIJK. What are the FIJKs? Structure constants of the group. Yeah, thanks. Okay, so then you solve, and if you've solved, then you can write down this kind of thing, the path out of the exponential, with these being the tangents along the path, Ti, the generators of the group, and that will give you the path, on the group. And then if you agree with Nielsen, or you think that Nielsen's idea will be pertinent for us to study continuum physics, then the complexity of this unitary, notice the complexity of a unitary because it's made some transformation. Like you're not interested in the state. You're studying what does the Hamiltonian do to states is what you're studying. Is then you compute the geodesic length in the usual way. Okay? It's easy to show that if the Hamiltonian is a simple operator, then this thing will grow linearly at earlier times. The reason is, this is a nice simple direction I'm moving in. It's not costing me anything, so I don't need to do anything else. I just keep following it. And if I simulate it, I also follow that direction, and it'll give me the same, it'll be the shortest way. No problem. So I'll get that initial linear growth we were talking about for free. Really, the only question is, when does it end? Right? So one way it can end is through geodesic loops on the unitary group. So you know perfectly well that SU2 is a sphere. So if you go past the pole, there'll be a shorter thing in the other direction. SUN is some much more complicated fiber bundle with sections that are hyperbolic, sections that are not hyperbolic. There are many complications there. So geodesic loops are actually difficult to calculate, and computing all the geodesic loops of SUN is an unsolved problem in math. Okay. However, there is actually another way in which these things can fail, using involving something called a conjugate point. Here's a conjugate point. Here's how you find a conjugate point. So what you do is you say, here's a trajectory, which is supposed to be geodesic, and then you perturb it. And if up to first order in the perturbation, it produces a new curve that satisfies the geodesic equation with the same boundary conditions, then you can show that you can push this trajectory further, and eventually it will settle into a deeper saddle, and that will be a shorter geodesic. So you can show that. So, okay, that really means...
Sorry, this second. So you have a geodesic between 2 points.
Yeah.
Then you push, I guess, one.
You push the trajectory. So you just start pointing this way. You start here and here. You aim it a slightly different direction, and then it goes a different way to the end.
Oh, to the same end.
To the same end.
To first order.
To first order.
So it's stationary.
Yeah.
Stationary in that particular direction. But to first order.
So then it's a saddle point.
Yeah.
So then you can slip it off the saddle point.
But how do you know it wasn't just a minimum?
There's another one which satisfies the same to first order.
Yeah.
So both minimal, I thought you have two minimal curves between the 2 points depending on which to the curve.
If it was a minimum, it wouldn't satisfy to first order.
Why?
It'd be zero.
Yeah.
Right? I mean, so at first order, it'd be second order deviations. A minimum would have second order deviations.
I thought because this is like a saddle point, all first order things don't change the action. All first order changes don't change the action.
It won't change the action, but if it has to satisfy the geodesic equation of this other thing. It's variations of variations.
Yeah.
Just like a second order. Yeah.
Okay, but then it could be like a
second order.
It could be like a 5 to the 4, plus 5 to the 4.
Yeah.
So it could be a minimum, right? Why? How do you know there was some? Sorry.
No, it's a good question. How do I know that when I'm doing this differential geometry context, it is a saddle and not...
I mean, let's start from the minimal guy. Let's say the minimal. Are you saying that somehow you know that the minimal guy deviates from things at quadratic order? There's some theorem.
There's some theorem of this kind, but I can't tell you what it is. The same fact appears in the proofs of the singularity theorems, actually. The same facts appear there, but I don't actually remember all the details as well.
Right.
But that is a fair question. And I can't quite answer.
Typically, you'll have just one geodesic, right, between two endpoints. So that's the more common.
No, it's a pretty. I mean, lenses you have many geodesics all the time.
All right. I mean, then you fine if you but it won't be like you'll have one family, right?
So this is not a family because there's a first order deviation.
One direction and a very specific other direction, is it?
So this you change the way
small deviation.
It's a small
It's
a small deviation, but there's some in the space of deviations. There's not any deviation that will do this. There's some particular vector direction in the space of deviations that you have to go in, and that can produce something. That's a little bit like saying you may be a minimum in many directions, but then you may be a saddle in others. And then, so if there is this is the maximum and this is the minimum, then as you go from here like this, as you go like this, it'll change character.
Right. So you're saying it's not that it happens that there was a 5 to the 4. There was a plus a phi square and b minus phi square.
Something like
and
that.
you balance it.
Something like this. Okay. Well, that could require some details of what is actually happening in the geometry, and that is not something I have full control over right now, so I can't tell you.
But what you're saying is it's representative of two geodesics meeting at the same point.
Mm-hmm.
How does it differ from geodesic loops? This always confuses me. Like, what is the difference between these?
Yeah. So these are geodesic loops that you are able to find. So first of all, at the tips, this doesn't have to be smooth, right? This can be like this. It can be like this. Right. The geodesic loop, you'd want them to be kind of smooth at the tips, right? There's a king. No, that's not the only difference. That's the king. That would be king. That would be king. That's the first thing. Well, maybe we can handle that, right? But the other thing is that this is discoverable locally. But these things, for example, if you go around this way versus this way, you're not going to discover that locally. There's no local saddle for it to slip from one to the other.
I see. Okay, but I understand there is another solution you see in perturbation theory, but it's not a family or something. There's just one other.
Yeah. There's no family of solution. There's another one.
And you're not near the other solution. It's just that there is a direction that
Yes, exactly. You're not near the other solution. Yeah. It's not epsilon. It can be a fair distance before you get to it, but there is a way to get there. So this is a way of discovering some of these loops. Okay. So, do I want to
So which metric are we working in at the moment?
This one.
This one.
We want to work in this one, where we want to compute these things in this metric, which penalizes supposedly complex directions in this space.
Okay. And so you've made some choice of what are complex directions.
Exactly. So that is the ambiguity here. We will eventually try to get rid of this ambiguity in a different way of thinking about complexity. But this is the state of play in this way of thinking. Yeah. So I'm going to explain the state of play. Yeah. And we'll see some nice results come out.
Yeah.
Okay. So do I want to talk about this? So, I'll put this up and just say some words and I just want to move quickly on. So, I should have also finished writing what I was writing. So let me write here, relevant. So there's a question of, why would you care about these conjugate points? Maybe they're very rare, or maybe they don't happen. Maybe you should look for geodesic loops. So there's some misleading intuition that goes around for why maybe these are not relevant, which is that
what was the conjugate points, basically?
The conjugate points were the ones you can find this way. The shorter geodesics that you can find them this way.
Okay.
So these are the global loops. This is a global thing. This is kind of a local thing. It's not really local. There's sort of a global difference between this geodesic and that geodesic, but it's discoverable locally. Let's say. So the question is, are these relevant? And so there's a sort of misleading intuition that goes around, actually, which Lenny used to talk about, that most sectional curvatures of Lie groups are negative. And so if you take as a model of a SUN, a high genus Riemann surface with the metric induced from the covering space, then you're going to find that there are no conjugate points at all in this toy model, hyperbolic everywhere. And so it's irrelevant. But this is actually not a good idea, because in Milnor's paper, the statement is that any right invariant metric on SUN must have some positive sectional curvature, or else it's flat. So it has lots of negative sectional curvatures. And so this sort of hyperbolic model where you have unique geodesics is good on those sections. But there also
so
it's a manifold, and the manifold, I'll take a submanifold. Submanifold. So if you take the submanifolds with positive curvature, so the trick here that's really going on is you can go on those things and come back on. So this is just a point that occasionally one sees this known fact that people know about submanifolds of SUN, but it's slightly misleading for this purpose.
So the statement is the average curvature is somehow negative.
It is also somewhat
positive minus.
Yeah, it's lots of negative submanifolds, negative direction submanifold, but there are some that are positive. And if you so happen to get lucky to find that along your trajectory or intersect that in the correct way.
Is there a sense of how rare that direction?
I don't know. Do you, Onkar? I haven't thought about that either. Right. So this might have been a response to some referee also, these people. So I don't know the rarity of these things. This is also, important theorems of Milnor in geometry. So okay. So how do you find these conjugate points? You find these conjugate points by you start with the linear geodesic that you start out with, as I said, along the trajectory of the Hamiltonian. You perturb it with something. You still solve the Euler-Arnold equation to first order. That gives some other simplified equation called the Jacobi equation. You just have to solve this. Now, the reason why little progress was made on this until fairly recently.
Euler Arnold equation is just geodesic equation?
It's a geodesic equation written in a particular set of coordinates in a particular way. The Euler Arnold equation, which we may have spoken about just before you came in.
But that was just rewriting of geodesic.
Yeah, that's it.
Yeah, geodesic equations are about manifold.
Yeah, but I'm using the using some arbitrary.
This one. This metric.
Left invariant.
Oh, it has to be left invariant metric, and we are using this one.
I think you just use the metric here, right?
Yeah, and we're using this metric, but the metric needs to have some property.
It's left invariant, but not also right.
That's correct. Yes.
So that gives you the play.
That's right.
I see. Interesting.
Yeah. So we don't have to go through the details of this. There's a certain amount of fuss and mess to write this down with local and non-local operators and how there are two equations that play with each other in some way and everything. So the reason why little progress was made on solving these equations over quite some time is because if I give you a general, if I give you a general metric on a group, these things are difficult to solve, right? Partly because the topology of the group is complicated, partly because just the equations are difficult to solve. So through the general genius of one Harikat and Kar and so on, we were able to prove many explicit results. So the way, if you can't solve equations explicitly, what you should do is you should find conditions under which solutions exist. I'll show that. And you can show many beautiful conditions that relate this formalism, which came out of computer science, to things we know and love in physics, which is the spectral properties of theories, right? That's what we're good at, right? Working out spectra and what they're like, etc. So there's a very nice relationship between the spectra and by the way, Onkar, I have decided that actually I gave some talk at Santa Barbara, and David Gross told me, you guys have proved this. It can't be a hypothesis anymore. So it's from now on, it's the criterion. Okay. We haven't really quite proved it.
Well, I mean, yeah, that was, it's like ETH, right?
Yeah, but we named it hypothesis in honor of ETH, but there's a criterion here. So anyway.
Oh, okay.
Yeah.
So I'm just trying to understand how much play there is in left invariant. So in SU2, in left invariant metrics.
Mm-hmm.
So in SU2, you can just deform the round metric by anything built out of the left invariant one forms, right? There are 3 left invariant one forms. So you get 6 parameters, 6 functions, or 6 parameters.
Yeah.
So it's a finite dimensional space.
I think so. I mean, it's basically like specifying some kind of a like a scaling form or something at the identity, the time space of the identity.
Mm-hmm.
And then once you know that, you can just move it around
by left
action. Yes.
I see.
You're trying to think about the degree of ambiguity in the definition.
How many left invariant?
Yes.
Left invariant. Yeah. So always a finite dimensional space, but one that grows like n squared, you say?
Yeah.
With SU.
That's roughly.
Yeah.
Yeah. And we are, of course, doing these things with some particular kind of choice of metric and expect that for some classes of metrics, including the various things that Adam Brown has written down, we're expecting results that look pretty much similar to this.
So I thought it was only n rather than n squared, because at the identity you can diagonalize this metric.
Yes.
And then there are only n numbers that you need to specify.
Mm-hmm. Oh, that's cool.
But the diagonalization, like the eigenvectors, can change, right?
Yeah. In SU2, it's 6.
The number of
Once you deform specific, because you have once you deform the diagonal,
the number of quadratic forms you can make out of this.
Yeah, exactly.
Okay, so let me just tell you some results. Really, this is not the notion of complexity we're going to wind up using, but I want to tell you some results which I think are interesting. How am I doing on time?
Oh, so it's 12:09.
So I still have another half hour.
Yeah, and usually the cutoff is only lunch. So, but it's
I have 1 hour and 29 minutes.
That's right.
Okay. So we'll just keep. You just tell me when to stop. Yeah. Anyway, it's 3 lectures. So
maybe one is
totally.
So all the theorems you're proving require only that the metric is left invariant.
Well, I wouldn't say that, because the way I think that's true, but we didn't show that. I think what we showed, Onkar is doing this, which means he thinks we showed that. But I thought everything that we demonstrated involved a particular choice of metric, involved a separation to simple and complex operators in a particular way.
That's right. I mean, so it's that's right. So Vijay, you were showing that metric, right?
Yeah. So strictly speaking, we're working with this metric, but I think everything we say will be generalizable to anything that involves a large penalty here and not so much of a penalty here.
But if you're going to work at that, say it a little more. Then unless you say something about alpha and beta, why is this left invariant?
Yeah.
This is like a half split.
This is just the matrix aspect.
Identity. And so if you want to do it at a different point, what you do is you pull it back to the identity and do it there.
No, okay. I'm saying that you've got this matrix, which is like an n square dimensional matrix.
Yeah, it's on the Hilbert space.
How much is in the first block? How much in the second block?
These are this is a square block of the simple operators.
No, but what does that mean?
As I said earlier, it was like maybe a few body operators, right? So
I mean, if you take an explicit example like an SYK model or something, and you can decide to say like, okay, up to 4 body interactions or simple, k body interactions or something.
So I thought we were doing group portion at the moment. So let's just talk about SUN.
Sure.
Yeah.
Because the maths is SUN, right? We don't know maths is SUN.
Yeah.
Okay. So in SUN, you just have to specify a size of that block.
Yes.
Okay. So you're saying some fixed thing as n goes to infinity?
So usually some fixed thing.
Yeah.
But your theorems work for arbitrary division?
Theorem, I think, works for arbitrary division.
Arbitrary division. Okay.
Yeah, you have to pick some of this like this and some of this like this. And so the criteria will work on the basis of these. I don't think we've carefully investigated if this bit scales with n. We have not, we've always kept this kinds of things as order 1 in the large n limit.
And why is that left invariant? Sorry.
This is just the matrix of the tangents.
Okay.
Then you pull it.
So this is what was
I see. So it's not even a question. Okay, thank you.
So if you look at this, it's getting transported around to other points.
And this SYK example, if it was just few body, then it's polynomial. It's not exponential. I mean, not in this end, but log n.
Yes, it'll be polynomial n because you can pick, for example, polynomial in the number of fermions.
Yeah.
Right? Because you can pick, if you're going to pick 2 body, I can pick 2, any 2. Absolutely. It can be polynomial. Absolutely. That's a very good point.
And left action on SUN is free action. There are no SUN elements that stabilize a particular point by left action.
Well, there could be, right? You can.
Criterion this. If every action moves one point to another, then we don't need to say. If there are some that stabilize the point, then it constrains what this thing is.
There will be, right? There will be some stabilizers because you can have something that acts on this and this separately. Because you can have an SU L times an SUK that can be a subgroup of this, namely acting on this and this separately. And those things will stabilize. Because this will act like the identity of those pieces.
No, but only identity stabilizes. There's no non-trivial SUN.
There's no non-trivial, I don't think, but that requires some thinking.
No.
This is the first time
it's like
years I've been asked these questions.
It's like a fundamental representation, right? Because left action is like acting on fundamental.
Yeah.
And fundamental.
Yeah, that's
Hopefully, none of those questions will turn out to be important for us. So I'm going to move on.
But just to ask, this much, so I keep in mind, the idea is that alpha beta pertain to simple operators.
Correct.
They're sort of smaller in number than the alpha dot beta.
Yes, and I said order 1, and Pratik corrected that it's going to be polynomial but not exponential in the number of degrees of freedom. Yeah, okay. Absolutely. Yeah, you want a parametric separation between the size of the Hilbert space and the number of these operators.
Okay.
Otherwise, you'll trivialize the problem, right? Because if it gets too big, the space where it's easy, then you can just go in any direction.
So this form of the thing preserves more than left action of SUN, right? It preserves.
I'm actually going to move on.
Okay.
Because this is taking us down a tangent that's interesting, but I don't think it's completely relevant.
Once you specify a mathematical problem, then we can analyze it.
Yeah, so I said,
understand the problem. How could we move on?
Okay, let's keep talking about this for the rest of the 3 lectures. Let's start.
It's better doing that than moving on without knowing what we're saying.
Most of the audience may disagree with that particular point, but okay, we'll keep talking about left invariant metrics. Okay, so here we go. We're talking about this metric.
This metric, apart from being invariant, it's also invariant under some combination of left and right, right? Because if that's N1 and that's N2, then SUN1 can SUN1 left and right.
Yeah, I know, but why is that relevant? This has to be left invariant. It can be left and right invariant, and I don't care, right?
So I'm trying to ask, your theorems will depend on what assumption? You're saying it depends on this one?
I'm going to restrict it and say it is a very specific theorem with no generality. It's for this metric.
Right.
I'm out.
I'm trying to understand what that means.
It's this.
What property of that, what you're saying? I'm trying to give an invariant statement about what you're saying.
Yeah.
I think just left it.
Just left it. Great.
I think I'm happy making a variant statement.
Yeah, I think it's just left. And that is basically everything follows from that geometric equation.
Yeah.
And that geometric equation was written from the
Okay, sounds good. I'm happy with that.
Only briefly, you're going to discover it in a minute. Yeah. But I'm going to say this is a completely specific, totally non-general theorem about exactly this metric in this form where this thing's found. That way I can cut off my, not display my full understanding of, or lack of understanding of these kinds of left invariant metrics. Okay. So having said that, here are some results. I'm not showing you how these were shown, right? They're basically kind of spectral criteria that lead to the existence of geodesic, sort of these conjugate points that cut off the complexity growth. Right? That's what I'm interested in here. So, okay, so suppose M and N are any energy eigenstates, and T alpha are the local read complex, simple, or few body, pick whichever kind of definition you want. And these are supposed to be the non-local ones. And the Hamiltonian is supposed to be built out of these things, okay, or some of these things. Then the linear growth and complexity will persist for a time that's exponential in the entropy of the system, which is extensive in the system size.
I'm really sorry, the Hamiltonian is built out of
the simple things.
Yeah,
simple things. Yeah. If the following is true, so you imagine any two energy eigenstates. This thing is a matrix element for transitioning from energy eigenstate N to M by the action of a simple operator. This is normalized in some way by all the operators. So this is telling you something about all the ways in which you can go from one state to the other state. And if this thing is exponentially suppressed, then it's true that your linear growth will persist for exponential time. The reason we're interested in that fact is, first of all, it's hard work to show that usually in most cases. So for example, for random circuits, that was only shown like 3-4 years ago by Jonas Haferkamp and Nicole Halpern and people like that. It's actually difficult to show a thing like this. And because that's the kind of phenomenon we wanted to see, very long linear growth, we wanted to see that in the gravity case if there were supposed to be a correspondence here.
So sorry, just to internalize, the point is that the term involving alpha dot in the denominator is much bigger. Is that right? This
effectively, yes.
2s.
Yes. Or another way, yes. But another perhaps way of thinking about it is that it's difficult to change one energy eigenstate into another energy eigenstate through the action of a simple operator. The reason why we call this eigenstate complexity originally hypothesis, now I'm calling it criterion, is because this is very similar in spirit to the eigenstate thermalization hypothesis. Things like this have been seen before, right? We say that things look thermalized. Things that thermalize have the character that simple operators can't change, energy eigenstates to each other. This is slightly different. There's two slightly different. There's some slight differences, but it's very much similar in spirit. So it's nice. It's satisfying that the similar physical criterion to the usual thing in thermalization has the effect that it'll make the quote complexity of the state persist for a long time. May give us hope that if I give you some appropriately complicated chaotic theory related to gravity, that I could see some effects of this.
And really sorry, where is the linear growth? So it's exponentially suppressed?
Yeah, so the idea here is you start out growing linearly because you follow the Hamiltonian. That's the shortest path. Then what you do is you ask, when will this get cut off? It will get cut off if you have some loop, some shorter path. The global geodesic loop, which I don't know how to compute, may cut it off. We can't say anything about that. However, we can compute when the first conjugate point appears. Right? And you can see that no conjugate point will appear for exponential time if this is true. So instead, you can check this spectral criterion on a theory instead of trying to solve the geodesic equations.
Okay, so that's
it.
I see.
So here's the second claim.
And so where does epsilon show up in this? There's some.
Yeah, so in the metric, I had the penalty involved in epsilon like this. I think I put an epsilon like this, did I? Oh.
It's the relative cost.
There should have been an e to the epsilon mu here. I'm changing notation to something like this. This epsilon was associated with the complexity penalty.
But it's some order one.
It's an order one number.
I see. So it persists for a time of order one? Is it
No.
E to the
entropy.
Got it. Okay.
So grows with system size in that way, but there's some coefficient there.
Got it.
Okay, so the claim 2 is that if I have an arbitrary local Hamiltonian with a finite complexity cost factor, you can show that conjugate points must exist finite distance along the linear GDZ. So that's a statement that you can show. What that tells you is that these kinds of conjugate points are relevant, as in they will eventually truncate your growth before you get to arbitrary time. So if this is the notion of complexity to be compared to gravity, then you will not get complexity growth forever. This is related to the earlier statement I was making about the truncation of everything. And you can, this is basically shown by example, you can try out integrable and chaotic systems. And for the two kinds of systems, you get the truncation occurs at polynomial versus exponential time. So that sort of accords well with what you might hope for, that things, integrable systems don't actually get that computationally complicated, but chaotic systems do up to some exponential time.
So the formalism for this proof was the setup you had.
Yeah, it was this thing, solving this Jacobi equation, and you basically need to try to find out when you have, you want to solve this, when do solutions exist? So this is solutions exist. So you check for when they exist, and you can show that they don't exist for a time of this order if this is true. So that involves a certain amount of manipulation, which I thought best not to go through because I actually want to go through details of the second notion of complexity. I want to talk about that.
Local generator means in the first block generator.
I'm using local to be equal simple, to be maybe equal to few body. I'm not really committing. This has to do with the earlier comment you were making, that it doesn't really matter what you've picked to be inside that block. Right? You were asking what do you have to pick inside the block? You don't actually have to. It's only just the structure of the metric matters, and the statement the Hamiltonian is built in that block.
So it's local means within that first square block.
Yeah.
Something which has an off-diagonal element between this and that is non-local.
We are talking about tangent directions that have been diagonalized at that entity. So the top block is simple. These tangent directions are simple, and these tangent directions are complicated. Because we diagonalized at that entity and wrote that. Okay.
And does ETH imply this?
Well, we weren't able to show that. So we tried for a while. Yes. So we actually spent some time trying to show that ETH automatically implied this. That would be nice. But it's slightly different in form. Like the normalizations, the extra e to the minus, there's some differences, and we weren't quite able to. We think it should, and we say some words.
You make a prediction for the numerator at least, right? Like if E alpha has this form, which is this random matrix, then it will give you some number.
Yeah, you can certainly stick in random matrix forms and get some answer, but I don't think we actually did that. Yeah. So here's the third claim. So again, this is the kind of thing that you do when solutions exist or don't exist. So if the Hamiltonian has an adjoint eigenoperator, and the eigenvalue is lambda, and this adjoint operator is in the space of quote local operators, then you know that a conjugate point occurs at a time like that. On the other hand, if the eigenoperator is non-local, then it occurs at a time like that, the conjugate point, where this mu is this complexity penalty, which, remember, is supposed to be extensive in the dimension of the Hilbert space. So it's huge now. So you can gauge when these things happen based on the eigenoperator, and so on. And you can put down other criteria. We don't need to go through all of these. Basically, I'm trying to say there's a whole bunch of things you can show that relate when the computer science notion of complexity growth will truncate in physical dynamics based upon certain kinds of spectral criteria. So I think this is the state of play. Not much more has been done with this, partly because, I would say from our point of view, okay, suppose you want to relate this to gravity. Expression is okay, what's the gate set of your field theory, right? Even if you're doing something simple like SYK, which is the place to try these things, JT, not gravity. There's you need to make some commitments. I'm not completely clear how to make those commitments as to what is simple, complex, etc. Okay, so this has gone slower than I had thought, but that's okay. Right? Because unfortunately, there's 3 lectures. Yeah. Right. So it's worth thinking about an alternate approach, because we don't know if there is a relationship to some notion of complexity, what that notion may be. So we should start putting other things on the plate. You'll see this one that I'm going to talk about turns out to, in the case of JT gravity, it turns out to be equal to the length of the wormhole turns out to be equal to this notion of complexity. And later on, we'll talk about what is the relationship in these 2 notions, and can you productively use them at the same time. There was a question there.
So in the claim to, it does look like right-order function with the conditions met and the finite initial expansion.
Yeah.
The point will reach.
Yeah. Yes.
The Jacobi equation is the right one.
Yeah. In fact,
what's the Jacobi field here?
It's this perturbation, right?
Okay.
The delta V. Yeah, the perturbation from the linear trajectory. In fact, again, the singularity theorems and the caustics that you get there, I think, are proved in the same way, as you say. Okay, so given that, well, we have results which are promising, and qualitatively it's going to reproduce what we want: exponential growth, linear growth for exponential time and everything. But hard to know how to fix coefficients. Is that I suppose we might have hoped in the beginning that through some intuition we would figure out what gate set to use, and we could fix coefficients. It's not completely clear. So we're going to try another approach, which is going to be much more elementary. And so we can actually fix everything because we put our money down, and then we can compare. So in this approach, I want to think about the complexity of a dynamical system in terms of the degree of ergodicity it has in some sense, right? Of course, ergodicity has been studied in many ways for a long time, but we will pick a particular way of going after it. So if I was talking about classical systems, what would I mean by simple integrable dynamics? Well, what I mean is that, presented correctly, the thing will go around in little loops in the phase space or something. So an initial state visits some finite dimensional subspace of the Hilbert space quantum mechanically is what I would kind of expect. What's a complicated or chaotic dynamics, I'd expect classically that the initial state sort of ergodically comes close to basically all points in phase space, Liouville theorem notwithstanding, and quantum mechanically somehow the state should explore the entire Hilbert space.
So here, when you say initial state, you have in mind a generic initial state.
I may mean a generic initial state. As we will discuss further, it will become interesting to consider which initial state should we consider. Because if you picked an energy eigenstate, obviously it goes nowhere. It just picks up a phase. So you mean some kind of generic initial state. Hasn't been specified yet. So we have to say what we mean. Also, you may say this is trivial. This is sort of weird to say it like this, because a pure state is always just a vector in the Hilbert space. So what do you mean? Well, we mean how we want to track its trajectory, right? We don't want to talk about, okay, so let me say a bit more, So in this sense, I want to talk about the quantum complexity. If you want to take this point of view, you might characterize the quantum complexity as the spread over the wave function over time in some basis, right? So you might choose to characterize it like that. In which case, it feels like there's an ambiguity, which is which basis should you pick? So I'm going to say, inspired by Kolmogorov and all these people, that we should pick for a given initial state in a state-dependent way, we should pick the basis that minimizes the spread over time. By the spread, I mean minimizes the part in this basis, how widely spread it is over the basis. So that's the way I'm going to define what I mean, right? Again, the idea here is the basis are the building blocks out of which I write the state. I want to minimize the number of building blocks, and I should pick. So now this time, though, I give myself the freedom to pick the building blocks that minimize the description, right? So I've given myself that freedom, and I'm going to pick that distinguished basis to minimize the description.
You're going to minimize once and for all, not like
once.
as a function of time.
I'm not going to do it as a function of time, because then if it's a pure state, it's a pure state, I can keep doing it again and again. I just pick always the vector. So I'm going to have to do this once at the beginning and then stick with that. That's the idea. Okay. And all right, and I'll define the quote spread complexity as the spread, as some measure of the spread of the wave function over time in the minimizing basis. So I'm going to think in this way. Okay, and we'll see if the definition is useful. Again, the perspective here is I want to express some concept, so I'm going to make up some notion, and it may or may not be useful. The usefulness of a new definition in mathematics is that it allows you to prove some theorems about things that you cared about or characterize things. So we will try to do that and discuss if it is useful or not useful. And there are related notions of spreads of operators, of course. This is Parker et al. Ehud Altman and friends have a nice paper on that.
And when you say minimize over time, like, is it at a particular time or?
I will define it. I will define it. What we will actually show is that for at least in at least some interval of time around t equals 0, it minimized the spread. The reason we can't prove it for all time, or we haven't proved it for all time, is we do this using Taylor expansions. Taylor expansions may have a radius of convergence, and we haven't characterized what the radius of convergence is for different quantum systems. If it's an infinite radius of convergence for the Taylor expansion, this is true for all time. And for discrete time evolution, everything I say will be true for all time. Trivially, you will agree with me that it is trivial. The difficulty is to prove it for continuous evolution.
And sorry, maybe already you're mentioning that in your last point, but this problem of how to define ergodic exploration, this must be thought about a lot in stat math. Right? I mean, it's at the basis of why
so much.
So there's a lot known.
There's an enormous amount known. There's an enormous amount, most of which I do not know. It's a long, long literature. Arnold has written things, although K and there's lots of stuff. So it turns out that the naive approach I'll describe appears to have been novel to the people in statistical physics, right? It's related to things other people have done. So one of our various works involved studying, this kind of thing in the context of, billiard systems, of which there's also a separate large literature, and indeed that's in some statistical physics journal to try to hopefully connect with some of the people there. So there's large literature, which I cannot tell you the details of because I don't know it, right, about this. Okay. But it seems to be that they think it's interesting too. Okay. I'm going to define the complexity, quote unquote, in this sense. And you'll see it's completely trivial to do, at least for discrete systems. So you'll agree with me it's correct. And then I will tell you we can do this for continuous things. So how would I do about doing this? From scratch, I would say here's the Schrodinger equation. The time evolution, well, it's e to the IHT, but that's a, some Taylor series like this. I can't guarantee for you the convergence radius, of course, but there you go. In discrete time, I simply apply the Hamiltonian n times. Okay, good. So suppose there is some orthonormal basis I have for the system like that. Okay, I'm also going to define, psi n in both cases to be the initial state acted on n times the Hamiltonian. You can view the continuous time evolution as the discrete time evolution summed up, with some coefficients that are functions of time. All right, and so what we're going to do is we will characterize how widely spread out the wave function is in this basis in terms of the probability of finding the state at time t in any particular basis element. That's going to be the obvious thing to do. And so I will have this distribution. There's the probability distribution. And then I can measure the spread of the distribution in many different ways. I could have, for example, measured the entropy of this distribution. I can exponentiate that entropy if I wish. I could say, okay, fine, I'm going to compute the kth moment of that distribution because, of course, the distribution can be equivalently characterized by its moments. Somewhat annoyingly, it'll turn out that the first moment, n, averaged over this distribution, so how far along in this basis you are, and this will turn out, by the way, to be an ordered basis. We're going to pick an order. I should have put here an ordered orthonormal basis. Okay, so it's ordered. So this n makes some sense, and you'll see what the ordering is eventually. So if I just take the first moment, it already turns out, actually that's the object that will turn out to be related to wormhole length in 2D gravity. So we'll come back to that. So the first moment. Surely the second moment and the entropy and other things and all have useful meanings, but haven't been extensively studied, and I will have not much to say about them. Okay. So anyway.
I'm thinking of H as being a simple operator.
No, here you don't have to think about H as anything.
Okay.
H can be whatever it wants.
Right, but if it's going to make some contact with your previous notion of complexity,
then you would want H to be a simple operator.
And should I think of psi 0 as being a simple state or a complex state?
Neither. I don't think it matters. Yeah. Let me explain why I'm saying this. I'm shifting the ground a bit. In the previous part, we talked about the time evolution operator and how complicated this was.
Yeah.
This is a more hybrid notion. It involves both the Hamiltonian and the state. And if you pick an eigenstate of H, the eigenstate could be structurally complicated, right? It could be very, very complicated. But its time evolution is very simple.
Right.
So you've pushed the complexity of the dynamics into the state. So one thing that I will discuss at the very end is trying to think about the structural complexity of these functions, right, of these states. So that's something I'm sort of very interested in, because I think that connects with some of the things I said about structural complexity of black hole microstates at the beginning. I can tell you about that shit as on a separate basis. So I think that's what connects. So I've been variously trying to think about how to think about that in this context, about how structurally complex are the energy eigenstates. There's approaches you could take. Maybe I'll say something on the third day about that.
Thank you.
So, okay, so this is, okay.
Like in the gravity example, for instance, this initial state ends up being like the maximally entangled state.
It can be. It will be.
One application of
one application that we will talk about.
Yeah.
Will be, if you take 2 copies of the CFT and you do maximally entangled states, then that would be the initial state. You do a one-sided time evolution, and then that you could compute the complexity of the state in this language, where the initial state is the vector 1, and because you just picked it as a basis element, and then you have to pick a bunch more basis elements for time-evolving states and entangled CFTs. That's what it looks like. And that is, in fact, the precise object we will look at to compare to the length of wormholes in the JT gravity. And that is the
entangled in something you will do.
You don't have
context, but yeah.
You want to maximize, if you want to microcanonical, you want to do that. Actually, in this context, if you want to compute this object, you don't even have to do that. You can keep it a canonical ensemble, because I will describe when we write down it. We will be able to write down a closed form expression, an integral expression for the spread complexity in terms of certain orthogonal polynomials. And when you do that, if you have a state that is in the canonical ensemble, the exponential downweighting of the Hilbert space thermal weight will take care of things, and you can just do the calculations. That doesn't always happen in other kinds of calculations, but in this kind of calculation, it does. So that keeps your life a little bit simple. I'll give an example of a recent paper I wrote with Johanna Edminger, Rathindranath Das, Herman Verlinde, and Jonathan Carl was the lead author. Basically doing that for 3D gravity using the density of states of Toriachi and Maxfield and Maloney, Wittenkamp. So it was exactly that.
In this example, the state was very complicated.
Well, depends what you mean.
I mean, it's not built out of single trace operators. Exactly.
Yeah. So, but the thing is that in this formalism, this is an attempt to avoid having to commit to a statement of how complicated the initial thing is, and simply talk about how it evolves. And some things evolve in a simple way, like energy eigenstates. Some things don't. So generic states won't, but maybe some things do. You can also have things like localization phenomena happening in the dynamic. Many things can happen. So it's trying to take a different angle onto the problem. Okay, so now let me show you that let me just prove to you what the correct answer is for discrete time. Yes, please.
State complexity is quantified by the large number of bases.
But the large number of what?
Large number of bases.
It's not the number of different bases. It's by it's by this. So what you have a basis. You have a basis. Here's the basis. So I write my wave function. It's spread out on the basis in some way. So then that gives you some probability distribution. In this case, spread complexity would be the mean position. along this chain. Yeah, it's like that. Okay, so let's do that. And I'm going to show you what the correct basis is in the discrete case and ask you to believe me in the proof of the continuous case. It's a bit more complicated. So the correct basis to use is something called the Krylov basis, which to my eternal shame, I did not know about until we wrote this paper with Pavel and Austin and Javier. So the Krylov basis is something that's been known since the 1960s. The Professor Krylov and Professor Lanchos worked all of these things out. Everybody involved in this kind of development was apparently Hungarian. Okay, and it's what you do is you do the Gram-Schmidt orthogonalization of the initial state, and what are the things, the elements out of which the state is built: A psi, H psi, H squared psi, etc. So you Gram-Schmidt this. So this is ordered, right? A one action, two action, etc. You Gram-Schmidt it. That's the basis. So okay, seems reasonable. Why? So you can easily, for discrete states, discrete systems, prove a theorem that you pick me any other basis, and if you write down the spread complexity defined this way, or if you try to do the exponential of this entropy, you can show that the complexity, quote unquote, computed in that way will be, at least for some duration, less than any other basis you pick. That's a proof that you can give. I will now give you the proof in the discrete case because it's trivial.
Right? Just to understand the statement, for all time, this is the claim that
no,
the best.
because I'm doing a Taylor expansion.
In this duration.
Yeah, what are the radius of convergence of your Taylor expansion is?
Confused because if I pick some T naught, which is in that interval, isn't there some other basis which just makes the complexity?
Yes. So again, the commitment.
Yeah.
The commitment is at the start of the dynamics.
Yes.
You have to pick a basis,
yes, and
then you have to describe the entire dynamics of that basis.
Sure, but if the goal was minimizing C of T naught,
the goal is to minimize the description of I'm not stating this absolutely precisely as a theorem here. But what you want to do, the statement is, you pick me a basis, you fix the basis.
Yes.
Right? Then in that basis B, you have to compute these complexity things
yes,
over some period of time.
Yes.
Whichever basis you pick, the answer you get, you fix the basis at the beginning, you don't get to change it, is going to be bigger than this. Right? Because
for all time in that window?
No, over that window.
Yeah. But how is that possible? Because if I picked some other basis which happened to be 0 at T naught, it could have been larger elsewhere.
Oh, so you want to do this?
Yeah.
Okay. Let's agree at T equals 0. You agree that you're going to pick it to be of 0 size.
What was
No, he's saying pick a lousy basis here. Pick a basis that includes this state. And then what will happen is that this will do kind of terribly, but at this moment it will go down. So he's trying to push me.
One basis optimizes all time is not trivial.
Yeah.
But you could have chosen one of your basis vectors to be what it was at T equals 0, the second basis vector to be what it was at T equals T.
Then probably beats it at T naught.
Right, at T naught.
Okay, so you want me to be much more careful in the statement of this
I'm trying to understand the statement.
Yeah. Okay, so let me see. How shall I be more careful in this statement?
Maybe you average over some time window, and so you want to do as best.
Yeah, we could probably do that or something like that.
Yeah, something like that, right?
So
this basis.
I mean, intuitively this seems right, because what you're trying to do is you're trying to keep the time evolution in your basis.
This is exactly what I'm going to say.
Okay.
So let me tell you
So
what
some
here.
version of this should be.
Well, no, this is precise, right? I mean, so he's asking me to state the theorem precisely because this is imprecisely stated, and he's trying to make me be precise. And I'm not being precise here. I have to figure out exactly what the correct wording is.
Maybe Onkar.
I was wondering whether you could just state it in terms of Taylor coefficients, like you fix your first basis vector. If you fix your first basis vector to be sign on, then of course at T equals 0, that makes the spread 0.
Yeah.
And you want to minimize the first Taylor coefficient, the second Taylor coefficient.
Yeah, if you take it in that way, then that will be the case, and that's what the proof is.
Okay.
So let's do that proof.
Yes.
And maybe that's the way to make the statement. Yeah. It's been quite some time since I looked at the precise statement, and I usually state it like this.
Okay.
And this is the second time I've been asked a question today that I've never been asked before, as in make this precise. Right. Okay. So indeed, the proof as such is exactly this kind of Taylor coefficient kind of way of thinking, which is to say, if at t equals 0, you want to minimize the description, you should pick the initial state. Now I'm forced to keep the initial state in my hand. And now I have a state evolves a little bit. I need to add something to describe the evolution. So I'll add the orthogonal complement. So now I have two states in my bin. And then I'll keep going in this way. This is for a discrete evolution. Obviously, this will keep things as small as possible, given that I've already committed to doing this in a time-by-time manner. Oh, that's going to be the answer. We want the answer to be true. We want to do this for every interval. Indeed, that's a little bit like what you were saying. You have to do this for every sub-interval. It's not just for the... So for every sub, you have to be able to do this for every sub-interval. So if it's true up to here, up to some time t, you want to be able to do it for any little t that's less than big T. So if you do that, you have when you start with t equals 0, then you have t equals 1. So you need to be able to do that. Then you need to be able to equal t equals 2. Then you do this at every step. So if you want to minimize at every step in that way, then as you expand the size of the interval that you want to work with, this will wind up being true. That's exactly. I think that's what you said. Yeah. So I think that's right. I think there's some careful way of saying that we would have said in the paper, but I'm saying this more colloquially. Okay, so the continuous version of this is more complicated to do for some of the reasons that are being revealed here. There's some analysis to be done. There's some more precise statement to be made and things like this. So there's some analysis that I won't repeat here. I ask you to believe me. It certainly seems natural.
But there is a similar argument even in the continuous case.
Yeah, you need there's a sort of page length word of epsilons and deltas of showing why this is the case. So.
But what is the statement in the continuous case?
The statement is the same thing, that what you should do if you want for any, I guess I should say, for any interval t bigger than less than t, where big T is whatever the radius of convergence is for the Taylor expansion of your Hamiltonian. It is the case that if you measure ck of t for any time in this way, you have to do this for any things, then it'll be less than any other basis you pick if you pick the Krylov basis as your special basis.
But that also seems a little hard for you to believe, because at T0 it can, like, I don't think such a minimizing basis exists.
Well, okay. So maybe what I will do, maybe what you would like is, my second lecture, instead of saying everything else for the application, maybe I should actually just talk about that proof in more detail, if that's helpful. We can do that.
We can talk about it.
Yeah. So I'll have to remember precisely the conditions and how it's shown. Yeah. Yeah. There is a minimizing basis.
You stated in terms of Taylor
coefficient.
Yeah. So let's state it in terms of
possible as a minimizing basis, because sometimes you can always choose one of the.
No, but that's not the problem, right? I mean, that's not the problem to be solved here.
No, but you're asking that it's true for all times less than a minimum. So that is impossible.
What is that?
You cannot find a basis that will minimize it for all times less than a certain time, right?
Maybe you want something like weighted over times, average.
No, you can definitely do that. You can definitely do that. But what you can do is, I think if you say that you have to do it for that's the same thing as saying this Taylor sequence. So if you start with t equals 0 and you want to do this in a small ball, then in a bigger ball, then an even bigger ball, then you're obliged to do this step by step, right? So certainly in this discrete case, you have to do this at t equals 0. You have to do this at t equals 1, given that you did it for t equals 0. You have to do this at t equals 2, given that you've done it at t equals 1. And it's just the continuous version of that.
So like your basis would fail spectacularly initially.
And so it would fail the conditions of the way this is being done. The proof is a proof by induction, actually. So it does it in the beginning, then the next step, and the next step, and the next step.
If it's a statement about Taylor coefficients, it's clear.
Okay.
But the statement about any finite time for an interval cannot be true.
No, I think the point is it already failed before you got that.
Yeah.
So if you look at 0 to 1.
It's already failed.
My basis had already failed the test, so you reject it.
Why? Because
that's what he's
yes.
You've got a huge Hilbert space. You choose all your vectors up to that, and then add your one basis vector.
No, but
maybe you've got let's say infinite dimensional Hilbert space, and you choose one of the basis vectors. We all do whatever else at the beginning. I don't.
The next step.
So you want to choose from time 1 to n. You want to pick the correct basis. Then you want to add this thing. But then it'll fail after that.
Yeah.
So then at the next time, what we will do is it'll be quick.
Just let's stop at this time.
No, let's not stop at this time, because you can extend this for as long a time as you want.
No, but what is the theorem? What is the claim of the theorem?
But the full bit.
Yeah, the theorem fails at that time.
Then the theorem fails at that time.
Finite times is very.
It's confusing, yeah.
Yeah, but then the theorem will fail at that time. But then what I can do is I can pick a basis for which this is, yours is lower, but then I can actually keep going, and then you'll find it this time. So you're trying to get me to say what is the maximum time at which I want to say this, and that is I would like to say for the discrete case, I'd like to say it for all times, right? So that this will be true at all times because the discrete case you don't have radius of convergence problems. So your basis, it will be better at one moment, but it will fail afterwards.
Yeah. It will fail once I hit the size of the Hilbert space. Right?
If n is finite.
To that I can always do this.
Yes.
Because I just have one.
No. That's not true. So suppose you have this, and for the first n ones, k ones, and then you pick your basis vector, which is not the correct one to pick, if you like. Then it is true that it'll go down to 0 there.
Yes.
But then once you evolve further, it's going to happen that it's not going to be lower, right?
No, now I now do branch limits at the next stage.
So you want to restart the process.
Yeah. Until you hit the size of the Hilbert space, there's no barrier. Right?
So you want to let this go for a bit, then you want to restart the process at another time.
I think Yeshiraj is saying at every instant you just choose the vector which happens to be the state.
No, but they're not orthogonal.
No, they're not orthogonal.
They're not orthogonal. It's not orthogonal.
No, but then you do the Gram-Schmidt with
No, but you have to Gram-Schmidt the ones before. If you pick this one, it's not orthogonal.
Oh, yeah.
The vector at that time is not orthogonal. It's not an orthogonal basis.
Okay,
So I think what you're saying is correct. It's not orthogonal.
It's not an orthogonal basis, right? I mean, so.
I didn't do a spread when you do the Gram.
Yeah.
Makes sense. It's literally doing what we're trying to do.
Yeah, I mean, this is what you're doing. Except you insist the basis elements you are orthogonal.
So state the theorem is that up to a certain are you choosing a time?
I don't know what for discrete cases you don't.
Yes, I don't think you have.
For discrete, there's no time.
Let's do discrete. So discrete,
But forever.
Okay, forever until
you hit the
Hilbert space size.
If there's a finite Hilbert space.
I see.
That
Okay.
makes sense.
You can have a continuous system with the discrete time evolution.
So, and this will minimize it for all times up to that. There will be no basis you can find at any previous.
If it's orthogonal.
No, but that it minimizes it for
All times.
no, but minimizes what?
This
This quantity, let's say.
But at each t.
At each
t.
At each t is impossible.
We
Because I can always find a vector that something.
Oh no, but it makes sense.
In this sense. Yeah, in this sense.
What's your statement?
Find a basis which first minimizes at t equals 1, then
Yeah. And then you have to do t equals 1 for every interval, shorter than the maximum interval, you have to do it.
Now I get it. Thank you.
I think that's what I said, but okay. Anyway, okay. Maybe I didn't.
think that's makes sense.
And just show that what did you minimize? That's C and
I guess-
So you can pick. So you can either pick this quantity or you can pick this quantity.
You're saying
Continuous time.
dictionary ordering, if I understand you right.
Dictionary ordering.
Dictionary ordering. You're saying earlier times are more important than later times.
Yeah.
You have to. You're giving an ordering.
If it failed
Yeah.
earlier times, you reject it.
Usually earlier times happen before later times.
Like previously, which word comes?
If it matched at the first letter, then you check the second. You don't
Yeah.
A later A doesn't matter.
Yeah. Okay, so with that notion of ordering this thing.
Yeah.
Okay.
Which is the notion of ordering.
Interesting.
Further digressions.
This is fun. That's why we have 3 lectures.
That's why you have 3 lectures, and that's why we've already gone long over today's lecture, but that's okay. Okay, it's good I didn't prepare more material. Anyway, so what we're going to do is, given these definitions, we need to know how to calculate the object. And we're going to see that these objects are actually, you can calculate them very, very explicitly, much more explicitly than the other notion that came out of computer science. So I'll discuss 5 methods for calculating it. Then I'll discuss 6 applications. And then I'm going to end with some discussion of perhaps a new understanding of effective field theory and semi-classicality, which is something we've been working on variously with Vivek and Onkar. And there's other things going on with Pavel and Joan. And Pavel. So I'll discuss some things from some work that's on. So there's 10 minutes, so I should be able to get through the first one, maybe the first and second example of how to do this. So the primordial, the original way of trying to do this kind of thing, as developed in books on quantum dynamics by Lanczos and by Krylov and others, is as follows. So there's a method called the recursion method. So what you do is you start with the initial state and call that the first element of this basis that you're trying to build. Then you construct, and I'm not explaining how one comes across this recursion method. We'll come up with better methods in a little bit. And there's a sort of recursion formula. Given K naught, how to generate K1, and then K2, K3, the basis elements. And at the same time, you wind up having to generate, to do that kind of this procedure, these numbers AN and BN, which involve matrix elements of the Hamiltonian in these states that you're building, and also some normalization coefficients to normalize your states. So these coefficients AN and BN are called the Lanczos coefficients, and the whole set of them is called the Lanczos spectrum of the theory, as opposed to the energy spectrum of the theory. So, okay, so this is the recursion method due to Lanczos. And if you sort of boil down what that says, it says the Hamiltonian acting on the nth basis element, these are called the Krylov bases, the Krylov basis element, has this form. It has a, some amplitude to stay in the same state, and it has two hopping elements, one to go backward, one to go forward. So in other words, the action of the Hamiltonian essentially is Markov, right? So you can write down a chain, and in that chain, you have things that go in the same place and forward and backward. And what's kind of the really beautiful thing about this, and the reason why people who actually try to simulate quantum systems have actually been using this kind of thing for a long time, they're using it for other reasons. They're using it because it basically reduces any quantum system at all to a one-dimensional chain. And so that's very helpful for simulating on a computer. So that's what people have mostly used this kind of technique for in the past. So we're going to use it for slightly different purposes.
So people actually use this technique for classically simulating quantum systems?
This has been done. So I found this out at some colloquium I gave in Germany, and there was a person there whose job in life is to do that. And he said, oh yes, we use these methods, so he taught me some things. So the challenge is the potential numerical instability of the recursion process. So the difficulties of all the work they do is trying to get a numerically stable algorithm. And so I'll describe a little bit of a numerically stable algorithm, how you do this. Because if you make small mistakes here in a recursion formula, small mistakes early can amplify the large mistakes later. So controlling that is the hard part. So, okay. So another way of writing this thing down, this Markov chain, is to recognize that what we have done is tri-diagonalize the Hamiltonian. Now, all of us learned in college that we should diagonalize the Hamiltonian to get insight. So it turns out that this I also didn't know until we did this work, is that you should tri-diagonalize the Hamiltonian to understand dynamics. Okay. So how do you tri-diagonalize the Hamiltonian? So now I'll describe a more numerically stable method than doing this. So now that we know that the job is to take a matrix, the Hamiltonian, and make it tri-diagonal, as opposed to diagonal, with a particular in a basis where I agree that a particular state, a particular vector, takes the form 1, 0, 0, 0. Right? That's our initial vector. There's a way of doing this. So if you look at an advanced linear algebra textbook, they will tell you that a tri-diagonalized matrix is called the Hessenberg form of the matrix. This all apparently has been well known, for linear, it's a very done field. This has been known for a long time, but I only learned this in the last few years, right? So there's something called the Hessenberg form, and you can transform through an efficient algorithm any n by n matrix to the Hessenberg form by a similarity transformation. The way you do this is through something called a householder reflection, which I also have not heard of before, which is some sort of manipulation in which you take a matrix, you transform it this way, transform it that way, you add two things, you subtract something else, and it produces a certain reflected form, reflected in some plane in the space on which this thing produces that. And you can manipulate this to find the Hessenberg form. This has even made its way onto Wikipedia, so we should have all known this. So this is and it's what's more, it's been implemented in Mathematica, and it's there in SciPy. So you can just you don't even have to implement it. You can just use it. The one thing that you have to be careful of is they assume a particular initial state. And so you have to do some work to make sure that if you have an initial state, you first transform to a basis in which you have that initial state like this. And also, when you do this numerically using these household reflections, sometimes you'll get these off-diagonal BNs to be negative. Usually, in this way of thinking, you want them to be positive. That's just a choice of phase in the state. So you've got to adjust a few things in the. So in case you want to do this and you use the numerical routines that are there, just be careful of a couple of points with this. But that's kind of cool. That means normal humans before the age of Claude could even write these things.
How unique is it? There's probably permutations, but
there's permutations.
Like, are there any non?
Well, the thing is that this has a particular ordering, right?
Yes.
So of course you can multiply by phases, you can do various things, but the phases have been here defined to be real in this way.
So does that completely fix it? So that's it. There was no degeneracy.
So is it unique?
Namely, is the Krylov basis the only to construct that tridiagonal form, given whatever positive P and I think it's
unique.
And some modeling.
Freedom is only having the choice of initials.
Yeah, that's.
You can pick the initial state, and that's a.
Yeah, once you fix the initials,
you have to fix the initial state.
Permutations, right? You can take 1, 2, 3.
Well, but there's an ordered.
Yeah.
It's an ordered basis.
Yeah.
So the basis is ordered, so that fixes that. Also,
You want to change?
Well, I was just saying, if I give you the matrix, then if you put it in tridiagonal form, I didn't know what the order had to be, right? Like you put in some order.
Yeah.
But there's some freedom in that. But other than that, there's no.
Yeah, you're asking. No, yeah, but he's saying.
Yeah. But diagonal is like unique, right? Up to the permutations. I was just wondering if there's more freedom because tridiagonal is less.
So I'm saying one example of a tridiagonal matrix is a diagonal.
Oh, so you're saying it's not unique?
Yeah.
Oh, that's what
it's from your point of view.
Well, here, if you exchange some of these things, then the jumping of the off-diagonal things will move around.
But the zero vector also won't be an eigenvector, so it's not obvious that you can use the diagonal form. But there's still some freedom as to do it here.
Yeah, there's probably some freedom, but you can't naively permute it because if you did, some of these B's would go over there, right? If you can't just naively permute, if you want it to be adjacent, next you want this to be next down, so there's going to be a restriction of that. Okay, so now we're going to expand these things, and you can compute the spread complexity. You can, you basically time evolve a state, you find this distribution on the basis, and then you compute the spread complexity. So this is the primordial original method. We are at 1, so maybe this is a good time to stop. Okay, this is a good stopping point because what I'm about to do. So let me just give you a preview of tomorrow. So I'm going to start by describing other methods. There's a slick alternative method where you recognize that something called the survival amplitude, the amplitude for a state to remain unchanged, is a generating function for the Long-Shor's coefficients. So there's a super slick algorithm to use that generating function, which is also closely related to the spectral form factor. And then you take that data, that's what we will discuss here, and then you do some derivatives and do some calculation, and you're done. So it's a very, very slick way. Then it turns out there's another way where if you tell me the density of states of the theory, so the diagonal version, if you tell me the density, slightly coarse-grained, so I'm talking about density of states, so you've probably coarse-grained the spectrum a little bit, then there's an integral formula you can write down that will tell you what the Long-Shor spectrum is. So I've written it with these things here. So to invert this, there's some numerical algorithm you need. So there's an integral formula that you can write down. Then I will discuss another method, which says that if you have a random matrix theory, which is everybody's favorite example, something goes chaotic, then you can write down, and in the same integral formula that I described works. This is for a matrix model with any potential at all. You could have a polynomial potential. You can write this down. And what's more, you can write down closed form formulae, well, integral formulae for covariances, right? The analog of level repulsion, covariances of the Long-Shor. So you get lots of very, very powerful technique. And then finally, I will describe that if you give me the density of states, it's possible to define a certain set of orthogonal polynomials, which use as measure for the orthogonality the density of states. And then you can write down a straight closed form formula of this kind in terms of those orthogonal polynomials that will compute this quantity that we call complexity as a function of time. So basically, this reprocesses spectral data into this object in some interesting way. And there are connections with things like the spectral form factor and other stuff that we know is good things to know. So that's what I would describe. It's sort of reorganizing that information in some way. And then those will be our methods, and then we will do applications. So that's what we will spend our time doing. We should ask questions because we didn't ask any during the talk.
Seems like everyone is hungry. So,
So I want to ask, so you started with Nielsen complexity because we wanted to show that it is competitive in doing the non-local operations, right? So how is spread complexity related to time function?
So I haven't discussed that at all. There are a few papers, especially by people like Ben Krapps and friends, trying to do that connection. It's complicated. So one way of trying to do it is to do the operator version of this thing. And then suppose that you look at the complexity of the spread of certain probe operators. And then you ask, and a complex Hamiltonian should cause the probe operator to spread quickly. That kind of thing. You should expect a complex Hamiltonian to cause these kinds of states to become very complicated quickly. So that, by and large, has not been explicitly related, except in one paper I know of by Ben Krapps and Marie de Klerk and Oleg Lunin. What's the last name? Through that. I don't remember precisely the results because so what they did actually is rather than computing the geodesic, which is difficult to do, they had some way of approximating the geodesic. They had some clever trick of approximating the geodesic. And then they related these quantities together. I can try to look that up. I can say a few words about them if you would like.
There's also, study perspective on the picture that I was looking of Altman, where maybe Harshad can correct me, where just in terms of connections, where the claim is that the growth of the Lankos coefficients with number gets related to the Lyapunov exponent.
So yeah, that's very early times here. So at very early times, the growth of the Lyapunov exponent is running out of power, basically, is related to the early time quadratic growth of those coefficients is related to the Lyapunov exponents, the OTOPs. I will mostly be interested in the very late times.
Like the spectral form factor.
Yeah, so I'll be interested in times that grow well beyond that, first polynomially and then exponentially in the system size, where specifically they would have liked to use that growth as a diagnosis of complexity. But actually, I think even an integrable theory, of chaos, of chaos. Mm-hmm. But I think even an integrable theory with the same density of states, which you can write down, if you give me your favorite chaotic theory with some density of states, I can construct an integrable Hamiltonian with the same density of states, but without the level repulsion you expect. So I'll show that later. So if you do that, you'll get the same quadratic growth. Maybe I'll show a picture here. So what will happen is the early part will look the same, but what changes is that, so if you compute this object, it sort of grows here, you get the quadratic growth is the same thing, Ehud and company. I can construct an integrable theory that will do that easily. But you see this peak that comes at some exponential time. If you wipe out the correlations, the level repulsion, it'll do this. So there won't be this peak. So we would suggest, I think I need to add a slide describing that, given this question was asked. So we would suggest that actually this is not characteristic of chaos, even though there's some relationship to the OTOC. Then that makes me wonder about the OTOC as a diagnosis of chaos, actually. But anyway, but it's this peak that is the diagnostic of level repulsion.
Usually we believe the OTOC just because it's related to commutators and so on.
Yeah, I know. I know. I have some confusion about that. Yeah. Anyway, this quadratic growth, they did relate. Mm-hmm. I'm just telling you we can get the same quadratic growth by taking a theory with no level repulsion at the same density of states.
So is it true for any method?
What's that?
When people talk about Lyapunov exponent, they talk about, they say that you can see this Lyapunov exponent for any object. Right? I mean, can you see that? If you take an integrable model with the same.
Okay. So that I don't know the answer to. So it may be the statement any operator may be important thing.
Also, I think from what you explained to me, this Lyapunov exponent is upper bounded by this coefficient.
Yes.
Yeah, it could be very small. Yeah, it could be. I mean, you could have an integrable system where it's just equal, right?
For sure. Okay. But you do have, but the quadratic growth you can construct a Hamiltonian with the exact same quadratic growth.
I agree.
So okay. So all right. So that's a good point. So since it's an upper bound on the OTOC, it doesn't mean it has to be equal to the OTOC. So you can definitely construct quadratic growth. Like basically, because this stuff here, this structure, this initial quadratic growth, and some part of the linear ramp, essentially depends on what the density of states is. The density of states translates into some Langshore spectrum, and if you coarse grain a bit, then you can keep that density of states while wiping out the level repulsion. And if you wipe out the level repulsion, then you can have a Poisson type spectrum with that same density of states, and then you can still get this quadratic growth. So it's a different piece of data, I would say, about the system.
And then, of course, I should refer many talks, but you mentioned that you have these beautiful formulas for a general polynomial random matrix.
I'll say more about that.
Yeah, but do you also have general results in the double scale limit?
Yes, of the SYK and the
of the SSS, but more generally, if you were talking about matrix theories.
Yeah. So I will have a description eventually of taking some double scale.
That is the limit of the usual case, but since it's
it's a special limit.
So
it's a special limit which at early times has a known classical description as JT gravity.
That's why I'm curious.
So I will use all of these formulae in the later part of the talk to apply to double scaled SYK.
Okay.
And which is supposed to be equal at early times to JT. Well, we'll call it gravity. And we will see that because we have all of these sort of integral formulae and closed form this and that, we can calculate the late time behavior, and it differs from what Berkouš, Simon, Navrolansky, and Lin and Shirson, Rabinovich, and everybody would have said, and there's a reason for that. So what those authors did is they had a beautiful, Berkouš, what was the middle author? Narayan, Simon, whatever, the first people who saw this. They had a really beautiful paper. That's a beautiful paper. And the way it works is they use some ideas that were there from statistical physics, some guy named Erdos, who's not the actual original Erdos, another Erdosian company, for using these things called chord diagrams as a tool for solving for the spectrum of the theory. And then by taking the double scaling limit, while they're taking the double scaling limit, they're focusing in on an order one part of the whole Hamiltonian. So this little piece on left as it's getting large n. And then order one can be extremely large, right? The order one can be 1 million. Order one can be 10 million. So they'll fix that size, and then they will later take that size to be very big. So you fix that size, you take the large n limit, that's the double scale limit, you pick the size, and then you make the size bigger and bigger. It's that order of limits. So what they're focusing on is the tiny edge of the Langshore spectrum. And where they are able to get by hand solve using these chord diagrams to get analytic formulae. And that shows in that regime, the spread complexity grows linearly forever. They're basically taking a classical limit of the theory, in effect. They're looking at this little edge. And they get the linear growth. The formula exactly matches this according to the double-scaled SYK JT gravity matchup. The formula is equal to the formula for the length. So that's all great. But if we agree that the world is actually large but finite n, then we can just use all our formulae for large n. And what you will find is indeed, if you take an order one piece, it exactly reproduces what they did, as it should. But then at late times, you get this plateau and this complexity, and that happens because the Langstroth coefficients change, the formula for the Langstroth coefficients changes from this growing ramp to something falling. And that turnover causes a saturation of the spread complexity. And then if you go back and ask in terms of the JT gravity, what was happening, you would say that the formula you wrote down is not very semi-classical anymore. It's describing a wave function that's completely spread out in some way over the scroll thing. So there's some sense, and it's very quantum mechanical. And then you could say, well, what did that mean? I could have changed bases to sort of make this very localized. And that's where the work that you folks have been doing, right, about the negativity is important, because you can evolve and then you can evaluate the Wigner negativity of the evolving quantum state, and it becomes very large. So you know it is definitely not classical. It's definitely very quantum mechanical. Yeah. So then that will form the basis of the statement that at late times, late here is not that close to the singularity. It's the time that the saturation is going to start happening. You can conclude that, well, if you agreed that you should simply extrapolate the formula from early times to late times.
I should wait, of course, but I would say once you go beyond the double scale limit, you're not really describing JT gravity, and we don't know if you have a gravity description.
No, at early times you do.
At early times, even away from the double scale limit.
A double scale limit is strictly n to infinity.
Yeah.
Well, so suppose
that's the exact equivalence,
right? So suppose it takes n very large.
Yeah.
Wouldn't you say that is an analogy with taking G Newton, not exactly zero?
Yeah, but I think the equivalence to all orders non-perturbatively in the genus expansion
that will have
established just at the SSS level, right? So if you take n to be very large but finite, you're going to have to modify JT gravity in some way. The question is there a modification gravitational? I don't know if there is.
Already at the disk, already even without worrying about the non-perturbative connections, you're already backing away from the double scaling limit. We know that this one, since it's called Hilbert space. I'm saying that the JT description becomes the relevant description in the double scaling limit. But you could back off from the double scaling limit while keeping n infinite. Work at n equals infinity, but back off from the double scaling. Already there we know that JT gets modified.
Yeah. So maybe you're saying that what should have been done, or what one could do, is to this sort of correspondence between length and the spread complexity, whatever that formula is being written down, that already should be modified at all times, because you should sort of modify JT gravity in the first place. Maybe that's what you're saying.
I mean, I know we have discussed this already, but I mean, the DSSYK model as a quantum mechanics model is very different.
Yeah.
But I don't know of understanding it gravitationally. That's all I'm saying. So these other corrections and all.
Well, you don't know how to understand it exactly gravitationally.
That's what I mean. Is it some high dimension operator? What is it?
But you might say the same thing about any ADS-CFT thing, right? I don't really know at any finite n of SUN Yang mills exactly what the gravity is. But I do know that if I take n large enough, there's some level of correspondence. It's not like you would...
Right, but then we have the deep brains and everything and so on and so forth. And all I'm saying is here...
Even without deep brains, I would certainly say that if you computed some correlation function in the field theory, that I would go and calculate the appropriate Witten diagrams and what have you. That's some quantum mechanics there. It's not entirely classical. And I would say that that's a useful thing to do.
Yeah, I agree. It's hard to check at finite n. I'm just saying, since this is a model which is simpler than n equals 4, etc., it would be interesting to ask if there are, deformations from the double scale limit, which you can map to deformations of JT. Something, but I couldn't make sense of that, to be honest.
I agree. But that's not what we will do. What we will do is we will say, suppose you have given me this formula for length, then which turns out to be this complexity in the double scale limit. I will agree that I have pushed away from the double scale limit. I don't know exactly what the gravity is supposed to be precisely. But I'm supposing at early times it's kind of okay, because, the calculations they did would have been up to some exponentially small correction, presumably similar. But then I will say, I'm going to use the same formula that was prescribed to me in the double scale limit, which I take to be a reasonable description of early times in the system. I'm going to take that formula and I'm going to ask how that formula acts at late times. And then that formula will be this formula of the spread complexity, and at late times it will saturate. Now, you could say that there are other completions you could have invented. So you could have taken this formula that was true in the double scale limit, and thus perhaps or presumably at early times even away from the double scale limit. And then you could say that there's some other correction you should have added to it that was missing double scale limit, and then that object acts differently. So you could do that. That would be a different non-perturbative completion of the object that you could study. Then we have to have reasonable ways of trying to do that, and we can certainly try. So one attempt in that direction was a nice paper by Gabor Sarosi, Mark Mazet, and Luca Liesu, in which what they did is they had a different attack on this. They took the JT gravity, that computed, we know many things about the spectrum and different limits and things like this. Let me see, they had some definition of length that came from computing two-point functions. I basically compute some two-point function of a heavy operator, and it's approximately equal to e minus g is equal. You take that as a definition. You take the log of a heavy two-point function and divide by some numbers, and that will give some measure of length, right? At least in some limits. Then what you do is they said, okay, great. Now what happens is the way this went is they said, well, I agree that non-perturbatively there ought to be a discrete spectrum underlying this with some level repulsion. And they had some clever trick for including that fact into their analysis, and they got some completion of the length, formula for length that would saturate. I'll have a little bit to say about that because their formula for completion of that looks very like the expression we'll get for the spread complexity in 3D gravity. So there's some similarities, not the same, but there's some similarities. I think there's some connection, which I don't quite know how to precisely articulate. So there will be some connection. So that's an example of an attempt at an alternate non-perturbative completion of a length formula. You could take our attempt and just say, look, in this limit, you already told me what the formula is. The formula is also perfectly well defined at large but finite n. Actually, it's defined even at finite n. I'm just going to go with the formula. It worked in the limit where we knew what length was. It worked, so I'm going to use this formula, and that object acts the following way. And whatever the theory of gravity may be, this object, if it has a dual description, that gravity theory will initially show linear growth and saturate. That's the statement. But it's a good point. We don't precisely know what the gravity is.
Or if it even exists. May not. It could be that you have a finite n definition which doesn't exist.
Well, I mean, let's hope not, because otherwise, if it's actually the case, it only exists at large, and this is a completely useless thing. I have to say, I know we're all technical wizards and really like technically beautiful, complete, careful things like double scale limit, everything. But if it's actually the case that there's no possibility of even inferring anything finite, and this is a really boring and stupid thing to do. I'm sorry.
It's much less interesting, but I'm just saying it needs to be established.
But it needs to be established.
Every finite n deformation does some.
Yeah, no, I agree with that. That I agree with. But if there is actually the doubt that we can't do anything at finite n, it's not a theory of gravity, it's even approximately it's an effective field theory that's defined, then it's a completely useless effort that the whole community is engaged in for 7 years or whatever it is. So at least that's the way I feel. You could say the same thing for ADS-CFT as a whole. We haven't established the bulk gravity exists because who knows how to do the full string theory of the space. So we are somewhat moving on a prayer.
I feel that Maldacena duality is better. Better on a better footing even at finite n, because the limit comes by looking at deep brains and the dual description, all of which makes sense for finite n.
No, but if you look
and
at
I don't have a corresponding picture in the JT case. So that's
though on the other hand, I think at least 3 people in this room have been doing that kind of thing from practically inception. And if you look closer, there are many doubts that you could have. The original arguments are a kind of they're an argument, they're not a proof. Right? They're a statement that you kind of accept that P branes and D branes are the same thing. You stack them up, you take a certain limit, and there's an argument that they kind of match up. Witten's later paper, of course, adds a lot of substance to that. because it shows so many things line up, the representation theory and so many things you can write down. But a proof would involve a statement that I take this field theory Lagrangian, do some collected fields, or change some variables, and suddenly I get this other description higher dimensions, or vice versa. That's what a proof would involve.
Sure,
And
I'm not saying this is a proof.
we have a person here who insists on precise definition of everything. And so from that point of view, a precise definition for me would involve that. And I don't have that. So I feel like it's all slightly doubtful. And
I agree. I mean, sorry, we must close, but I just mean, actually
we can go further.
possibility is more finite for me. There's a greater possibility in 2D because, as you said, these are such simple theories.
No, we would like to, it should
On
be
the
shown.
closed string theory side,
I'm agree.
PS5, I don't even know
I agree with the statement that it is an important goal for the field in the case of 2D sort of gravity to actually show this at finite n. I agree with that statement.
And I'll just say one last thing. This for me is the crucial thing in trying to build de Sitter holograms, because the de Sitter case, you've got to explain the finite entropy of de Sitter space. And you only get that at finite, in a large finite n model.
So I can wax lyrical on why I'm even less sure about de Sitter space, right? I mean, so you and I have been around the block enough to remember a time when the hot thing to do in string theory was to show why de Sitter space could not exist, because it would always be unstable, right? That was an actual activity in which I suspect we have personally participated, right?
That still is a hot thing.
But for different reasons. But for different reasons, right? Now we have that's a one-dimensional Hilbert space. It's confusing. So all I'm saying is that I think de Sitter space and holograms of de Sitter space are also an activity. It's been a long time. There's a sort of recurrence in the field. Every some number of years, everybody will think about holograms for de Sitter space, and they will rediscover some fraction of the same actual problems, right? And then we confuse ourselves again. And there's a little bit of progress. So there's progress going on now. But I think it's much dicier, and it's not at all clear to me that solving JT gravity completely is going to teach us how to do de Sitter space. In fact, I think that there's deep conceptual problems. Like the size of the Hilbert space is, to me, a really deep conceptual problem. You've written a lot about this kind of thing with your baby universe and stuff. I think that's really confusing to me. And the thing about holograms, where is even the hologram, right? Past infinity, in that case, you need time to be emergent. The horizon, I don't know what that means, because the horizon is a fluctuating surface. So there's all of these things I find very confusing. And there's certainly not going to be an ADS-CFT like local dual and that kind of stuff, amongst other things, because if you look at the representations of the conformal group, which are realized past infinity, let's say by a scalar field, they're non-unitary. So what's going to happen is if there is a dual associated with it in some way, it will not look like the usual dual. It can't. Right? And I mean,
let's talk about some of the statements.
I think
I think this sounds like a great lunch.
I mean,